From the moment the universe drew its first breath, two presences began shaping everything that would follow. Gravity, the silent sculptor of space and time, and light, the swift messenger racing through the cosmos, began their endless partnership. Together, they are the architects of galaxies, stars, and worlds, and without them, there would be only darkness and emptiness. Their relationship is not one of competition, but of interdependence. Gravity bends and guides, while light reveals and informs. Every story we tell about the universe is written in their combined language. To understand gravity, we must imagine space not as an empty backdrop, but as a fabric that can curve and fold. Albert Einstein showed us that massive objects like stars and planets press down on this cosmic fabric, warping it so that other objects move along the curves. This is what we feel as gravity. It is not an invisible force pulling at us, but the natural path we follow along a distorted stage. The Earth orbits the Sun, not because of a mysterious tug, but because the Sun's mass has reshaped the space-time around it. Earth is simply following the straightest path it can find in that curved environment. This idea was once strange and counterintuitive, but time and experiment have confirmed it beyond doubt. Light, on the other hand, is both wave and particle, both rhythm and spark. It carries energy across vast distances at a finite but astonishing speed. It is the fastest thing in the universe, so fast that nothing else can overtake it. It defines the maximum speed limit of reality. Light not only illuminates but also informs. Every photon that reaches us from a star or galaxy is a messenger from the past, carrying with it information about the conditions of its birthplace. When we gaze at the night sky, we are not seeing stars as they are, but as they once were. Light is the record keeper of the universe, writing history in every direction. The interplay between gravity and light is what gives us our vision of the cosmos. If there were only gravity, the universe would collapse into darkness, with matter clustering into invisible knots. If there were only light, energy would race outward without form, unable to build anything lasting. Together, however, they shape and reveal. Gravity sculpts galaxies, forming dense clusters of stars, while light escapes from these furnaces, carrying their story to us across unimaginable gulfs of time and distance. The two weave the tapestry of reality in tandem. This relationship also defines our place within the cosmos. We live on a small world, orbiting a medium star, and every day we experience gravity's steady grip and light's life-giving warmth. The same rules that guide the Earth around the Sun also guide the stars around the centers of their galaxies, and even galaxies as they swirl together in colossal clusters. The same light that nurtures life here also journeys from the most distant reaches of the observable universe, bringing us news of events that happened billions of years ago. In this way, gravity and light not only shape the physical structure of the cosmos, but also shape the boundaries of our knowledge. They determine what we can see, what we can measure, and what we can imagine. The beauty of their partnership becomes clearer when we think of how they reveal one another. Gravity bends the path of light, curving beams around stars and galaxies so that we can see objects hidden behind them. This bending, subtle on human scales but profound across the cosmos, acts as nature's telescope. At the same time, the behavior of light tells us about the nature of gravity. By watching how starlight curves or shifts, we measure the strength of gravitational fields and test Einstein's predictions with astonishing precision. Light and gravity are not isolated actors but conversational partners, each telling us more about the other. The scale of this partnership is staggering. Consider the birth of the first stars. In the young universe, gravity gathered primordial clouds of hydrogen and helium, squeezing them until nuclear fire ignited. Light then burst forth, filling the darkness and announcing the dawn of cosmic structure. From that point forward, the two forces wove their pattern again and again. Gravity created dense knots of matter, stars, and galaxies, and light streamed outward, shaping the environment and guiding the growth of surrounding regions. The history of the cosmos is nothing less than the dialogue between these two presences. Even in our daily lives, their influence is immediate. The very concept of time is measured by the rhythm of light. Atomic clocks, our most precise instruments, rely on the oscillations of light emitted by atoms. Yet those clocks tick differently, depending on gravity, running more slowly near strong gravitational fields. The partnership of light and gravity is not confined to cosmic scales. It touches the very seconds of our lives, determining how we measure reality itself. The wonder of this relationship is that it is both familiar and alien. We know the feel of gravity, the steady pull that holds us to the ground, yet the truth of its nature as curved space-time is stranger than any myth. We know the comfort of light, the warmth of the sun, yet its dual nature as both particle and wave continues to puzzle and inspire. And when these two come together, they give rise to phenomena so astonishing that they seem to belong to the realm of dreams. Stars collapsing into black holes where light itself cannot escape, galaxies bent into distorted shapes by gravitational lensing, the universe expanding with light stretched into red as space itself grows. These are not fictions. They are the natural consequences of the cosmic architects at work. To grasp the full majesty of their relationship, we must see them in action. We must follow light as it journeys through curved space-time. Observe how gravity bends it, traps it, or stretches it, and witness how this interplay reveals the universe in ways nothing else could. This is the journey ahead, the unfolding story of how gravity and light, the twin architects, carve the cosmos we inhabit. And so, to understand how they shape the universe, we must watch them dance together across the grand stage of space and time. Gravity is often imagined as invisible chains pulling objects toward one another, but its true nature is far more elegant and profound. Einstein's vision showed that massive bodies reshape the very geometry of the universe. Imagine placing a heavy sphere on a stretched sheet. The fabric dips and curves, and smaller objects roll toward the depression. This is only a two-dimensional metaphor, but it helps us picture what happens in four-dimensional space-time. Planets, stars, and galaxies do not feel a tug in the traditional sense. They follow the straightest possible lines, but those lines themselves are curved by mass and energy. This insight replaced centuries of thinking about gravity and opened the door to a deeper understanding of how the cosmos works. Light, unlike matter, has no rest mass, yet it too obeys the structure of space-time. Photons always travel at the same speed, but their path is determined by the geometry they move through. When light passes near a massive star or galaxy, its trajectory bends, not because it is pulled, but because space-time itself is bent. This is why light from distant stars can appear shifted or doubled when it grazes the edge of another celestial body. It is also why the universe itself is like a grand hall of mirrors, with light weaving around unseen masses, showing us both direct and distorted visions of reality. The relationship between light and gravity is not merely an abstract concept. It is measurable, testable, and confirmed by observations. In the year 1919, astronomers traveled to remote locations to photograph the stars during a solar eclipse. The darkened sky revealed stars near the edge of the sun, and their apparent positions shifted exactly as Einstein predicted. This moment was more than a triumph of mathematics. It was proof that light, the messenger of the universe, listens to the voice of gravity. From that day forward, our picture of reality could no longer be confined to the simple pull of Newtonian forces. The cosmos was a living fabric, dynamic and curved, and light traced its shape like ink flowing across paper. As the decades passed, technology refined our view. Today, satellites orbiting Earth rely on corrections for both special and general relativity to keep global positioning accurate. Without accounting for the way gravity alters the passage of time, your phone would be lost by kilometers in only a single day. This is gravity and light at work, not in distant galaxies, but in our daily lives. It is humbling to realize that the same rules guiding starlight across billions of years also guide a traveler searching for a street corner in a modern city. The cosmos is consistent across scales, from the cosmic web down to the devices in our pockets. The interplay of these forces also explains why we can never see the universe exactly as it is, only as it was. Light requires time to travel. The sun is 8 minutes away at light speed, so we always see it in the past. The Andromeda Galaxy is 2.5 million years distant, meaning every photon we catch tonight began its journey before humans walked the Earth. The most distant galaxies observed are seen as they were more than 13 billion years ago, their light stretched into faint whispers by the expansion of space. Gravity controls the shape and destiny of these galaxies, while light carries their memory to us across the ages. Together, they bind history into the very sky. Even the colors of light are altered by gravity. When photons climb out of a deep gravitational well, such as the surface of a massive star, they lose energy. To us, they appear redder, their wavelength stretched. This gravitational redshift is another signature of the partnership. Gravity can change not only the path of light, but also its frequency, subtly altering the message it carries. Every spectrum we record from distant stars bears this signature, a reminder that the universe is not static but shaped by the silent dialogue between mass and radiation. At the largest scales, this dialogue determines the architecture of everything we see. Gravity gathers matter into stars and galaxies. Light pushes outward from those same stars, carrying heat, energy, and information. Without gravity, the early universe would have remained a uniform soup. Without light, it would have stayed dark, lifeless, and hidden. The balance between these two has given rise to complexity. Gravity forms the stars, light escapes them to seed the cosmos with energy, and together they create the possibility of life. Every breath we take is part of this ancient collaboration. The atoms in our bodies were forged in stars, whose fusion shines outward in light, while gravity held those stars together long enough for creation to occur. This partnership is ongoing and unending. When we look at the night sky, we are witnesses to a living story still being written. The spiral arms of galaxies are shaped by gravity's invisible hand, while the glowing stars within them paint those arms in light. Nebulae drift like luminous clouds, sculpted by stellar winds and gravitational tides. Black holes warp light into eerie halos, revealing their presence by what they conceal. Even the faint cosmic microwave background that bathes the universe is the afterglow of light released when gravity allowed matter to cool and settle into its first structures. Every layer of the cosmos, from the nearest planet to the most distant horizon, is the result of this dual narrative. The awe deepens when we realize that light itself defines the horizon of what we can know. Because nothing moves faster, we are bounded by the distance light has traveled since the birth of the cosmos. This is why astronomers speak of an observable universe. Gravity may bind galaxies beyond that limit, but we will never see them, because their light has not yet reached us. Our entire cosmic vision is framed by the race between expansion and the speed of light. It is both a gift and a boundary, reminding us that the cosmos is larger than we can ever observe, yet also giving us a way to trace its vastness. The story of gravity and light is therefore the story of possibility. It is the reason the universe has structure instead of chaos, illumination instead of darkness. It is the foundation of our sciences and the spark of our imaginations. To think of them separately is to miss the point, for each reveals the other. Gravity without light would be a silent sculptor with no witness. Light without gravity would be a restless wanderer without form. Together, they are the architects of reality, weaving the cosmos into a stage where time itself unfolds. And yet, their most dramatic encounters lie ahead in our exploration. Light not only bends, but sometimes becomes trapped by gravity so extreme that even photons cannot escape. In such places, we glimpse the ultimate union of these two forces. To truly understand their power, we must follow light into the depths of curved space, where its fate is sealed by the strongest grip of gravity. The most dramatic encounters of light and gravity unfold in places where ordinary intuition breaks down. Imagine a star many times more massive than our Sun, exhausting the fuel that sustains its fusion. When the outward pressure of light and heat collapses, gravity wins, crushing the star into an object so dense that even light cannot escape. The event horizon forms, a boundary from which no information can return. From the outside, it appears as a perfect darkness, a hole in the fabric of the universe. Yet the story is not silence. Light approaches the boundary, circling in unstable orbits, forming what scientists call a photon sphere. To a distant observer, matter spiraling inward glows fiercely, releasing energy as it falls. even in the face of annihilation, light narrates the final moments before disappearing forever. These extreme regions show us that gravity is not merely a sculptor, but a gatekeeper. By controlling light, it controls information itself. What we cannot see beyond the event horizon may hold secrets about the ultimate laws of nature, including the unification of gravity with quantum mechanics. And yet the very invisibility of black holes makes them paradoxical beacons. We know they exist because of how they influence light around them, warping backgrounds into luminous rings and flaring jets that travel thousands of light years. Their shadows are written in light, proof that gravity's grip can even shape absence. In 2019, astronomers unveiled the first direct image of a black hole, the supermassive object at the heart of galaxy M87. What we saw was not the hole itself, but the glowing ring of light bent around it. It was a portrait painted by photons that had traveled for 55 million years before entering our telescopes. This image was not just a triumph of technology, but a revelation of the partnership between gravity and light. Gravity sculpted the darkness, light illuminated its edge. Together, they revealed a truth once confined to equations and imagination. Humanity glimpsed the frontier, where physics meets mystery. Beyond black holes, the everyday passage of time itself is shaped by this partnership. Clocks tick differently depending on their position in a gravitational field. Light defines the rhythm of those clocks through atomic oscillations. Yet gravity alters that rhythm. An atomic clock placed on a mountain will tick slightly faster than one at sea level, because gravity is weaker at higher altitude. This has been measured with exquisite precision. Time, which we often think of as absolute, is shown to be flexible, shaped by the invisible hand of gravity and measured by the steady beat of light. Our perception of reality depends on this interplay, as if existence itself is written on a shifting canvas. Even communication across space is touched by these rules. Signals from satellites, traveling as beams of light, must account for the warping of space-time caused by Earth's mass. Without such corrections, navigation systems would falter. Our technology works only because we have embraced the truth that gravity and light do not act in isolation. They converse constantly, influencing not only galaxies but also the devices we hold in our hands. The science that keeps us oriented on our own planet is the same science that maps the cosmos. The further we look outward, the more profound the partnership becomes. The cosmic microwave background, the faint afterglow of the Big Bang, is light released when the universe was only 380,000 years old. Gravity has since stretched and warped that light, turning it into a map of the universe's early structure. By studying tiny variations in this glow, we learn how matter clumped under gravity's influence and how the first galaxies emerged. The interplay of light and gravity has preserved for us a fossil record of creation itself. Each photon carries the handwriting of the cosmos. This record also allows us to see the invisible. Dark matter, which neither emits nor absorbs light, reveals itself only by its gravitational influence. Light passing through clusters of galaxies bends and distorts in patterns that betray the presence of unseen mass. Without this lensing effect, dark matter would remain hidden forever. Instead, light once again plays the role of messenger, exposing what gravity alone conceals. The fact that we can map the invisible universe through such methods is a testament to the extraordinary union of these two forces. They grant us eyes beyond the ordinary, a way of seeing what cannot otherwise be seen. As we trace this story, it becomes clear that gravity and light are not separate chapters but a continuous script. They define the cosmos together, shaping its form and revealing its secrets. The universe is not static, it is dynamic, expanding and evolving, and this too is revealed by their dialogue. Light stretches as space itself grows, shifting toward red. Gravity struggles to hold galaxies together against this expansion. The push and pull between clustering and dispersal is the engine of cosmic history. We live in the tension between these two presences, balanced in a universe that is both bound and unbound. The wonder of their partnership is that it not only explains, but also inspires. To contemplate a photon's journey across billions of years, bent and delayed by gravity's hand, is to confront the vastness of time and space. To realize that we can catch that photon in a telescope and learn from it is to recognize the privilege of being conscious observers in such a universe. Gravity shapes the stage. Light tells the story. Together, they weave the grand narrative of reality. And to follow their tale further, we must step beyond our immediate world, watching how light bends and curves in the dance of space-time, revealing the deeper order of the cosmos. The universe is not built on a rigid foundation, but on a flexible stage. Space and time are not separate, immovable backdrops, but part of a single fabric that can bend, stretch, and ripple. This revelation, gifted to us by Einstein, is one of the most profound shifts in human understanding. To imagine space as curved is difficult, because our senses are tuned to a world where distances feel straight and time seems constant. Yet the evidence tells us otherwise. Every motion we see in the heavens is guided, not by invisible chords of force, but by the geometry of space-time itself. Planets circle stars. Stars orbit galactic centers, and galaxies move through the cosmic web because they are tracing the curves carved by mass and energy. Einstein's equations predicted that light, the swiftest traveler in the cosmos, should also obey this geometry. Photons do not have mass, yet they follow the same geodesics as planets and comets. They race along the straightest possible lines, but in curved space-time, those lines themselves bend. This is why a beam of starlight grazing the edge of the sun veers slightly off course before continuing on its journey. The effect is small, invisible to the naked eye, but measurable with careful instruments. And it is precisely this bending that transformed Einstein from a theoretical visionary into a figure of global renown. In the year 1919, during a total solar eclipse, astronomers led by Arthur Eddington photographed the positions of stars near the darkened Sunday. Their apparent locations shifted just as Einstein's theory predicted, by an angle too great to be explained by Newton's framework. The news spread across the world, accompanied by headlines declaring a new revolution in physics. For the first time, humanity had direct evidence that space itself was curved, and that light traced those curves with unerring fidelity. It was a triumph of human imagination, confirmed by nature, and it remains one of the most celebrated moments in the history of science. The bending of light is not a mere curiosity, but a fact that shapes our daily reality. Consider the network of satellites orbiting Earth that provide positioning and navigation for billions of people. The signals they send are beams of light in the form of microwaves, timed with exquisite precision by atomic clocks. Yet those clocks tick differently in orbit than they do on the ground, because gravity alters the passage of time. If we ignored Einstein's corrections, our maps would drift by kilometers each day, rendering the system useless. The global positioning system is, in effect, a daily experiment confirming that light and gravity dance together exactly as relativity describes. This subtle interplay shows that the universe does not separate theory from practice. The abstract equations written on chalkboards in the early 20th century now live in every pocket and every car. Without them, airplanes would stray off course, rescue operations would falter, and financial systems synchronized by satellite would lose their rhythm. We are all participants in the dance of curved space, guided not only by Earth's gravity, but by the light that navigates our lives. Yet these effects, though profound, are only a hint of the cosmic scale. If a small planet like Earth can bend time and shift the pace of light's rhythm, imagine the spectacle when entire stars and galaxies enter the stage. Light does not simply bend slightly, it arcs dramatically, creating illusions of multiple images, arcs, and halos. It can be magnified or delayed, revealing structures otherwise hidden from us. The bending of starlight by the sun was only the beginning. The true wonder lies in the vast theater of the universe, where gravity sculpts space into living lenses and light performs its ancient choreography upon them. To explore this, we must look further, beyond the nearby planets and stars, to the colossal structures that span millions of light years. It is there that gravity and light reveal their full artistry, transforming the cosmos into a gallery of distorted galaxies, cosmic mirages, and magnified echoes of the deep past. The dance of curved space does not stop at prediction and proof. It becomes the very tool by which we extend our vision, peering deeper into time and space than would otherwise be possible. When we think of light traveling through the universe, It is tempting to imagine it as moving in perfect straight lines, like arrows flying across an empty void. But the universe is not empty, and the stage it provides is not flat. Every star, every planet, every cloud of gas, and even every invisible cluster of dark matter presses against the fabric of space-time, sculpting curves that light must follow. The dance of curved space is therefore universal. It is not reserved for distant wonders, but is happening everywhere, even here, even now. Consider once again the simple act of watching the sun rise. The light that paints the horizon with fire has already been bent by Earth's atmosphere, but it has also traveled along the slight curve of space-time caused by the planet's mass. The difference is tiny, almost imperceptible, but it is real. When you lift your eyes to the night sky and see a star, you are not seeing it where it truly is, but where its light has been guided by the distortions along its path. Every photon reaching your eye has traced a history of interactions with the curves of space. Each star is not merely shining. It is telling you a story about the gravitational landscape between you and its source. This bending becomes extraordinary on larger scales. Imagine a massive galaxy containing hundreds of billions of stars sitting between us and an even more distant galaxy. The light from that background galaxy does not travel in a simple line. It flows along the warped paths created by the foreground mass, splitting into multiple images, stretching into arcs, or forming a halo of light known as an Einstein ring. These cosmic illusions are not tricks of the eye, but precise consequences of geometry. They are the dance of curved space made visible. Without them, many of the most distant galaxies would remain invisible, too faint to be detected. Instead, gravity acts as a magnifying lens, allowing light to deliver messages from realms billions of years away. Astronomers now use these natural telescopes to peer deeper into the past than any man-made instrument could reach alone. By observing how background galaxies are distorted, we not only learn about the galaxies themselves, but also about the mass of the objects bending their light. This includes dark matter, the invisible substance that makes up most of the mass in the cosmos. Light does not interact with dark matter directly, but gravity ensures that its presence is revealed. In this way, the bending of starlight is more than a curiosity. It is one of our only tools for mapping the unseen skeleton of the universe. Without the dance of curved space, the cosmos would remain largely unknowable. The precision with which we can measure these effects has grown astonishing. Satellites and ground-based observatories now detect distortions so subtle that they change the shape of a galaxy's image by less than 1%. Yet these tiny shifts, spread across millions of galaxies, allow us to map the distribution of matter on scales far larger than any single cluster. It is as if the universe has provided us with a grid of light beams, and by reading their distortions, we reconstruct the shape of the invisible floor beneath. What began as a theoretical prediction has become the foundation of modern cosmology. Even time itself is caught in this dance. When light is bent around massive objects, its journey is longer than it would have been in empty space. This means that different paths of light from the same background source can arrive at Earth at different times. Astronomers have observed quasars, distant blazing beacons powered by black holes, split into multiple images by intervening galaxies. The brightness of those images varies in synchrony, but with delays ranging from days to weeks. By measuring those delays, scientists can calculate cosmic distances with remarkable accuracy. Once again, light and gravity are not separate actors but partners, revealing the universe in harmony. It is worth pausing to imagine what this means. The night sky is not a flat dome, but a shifting stage of distorted visions. Each star, each galaxy, each glowing arc is not only where it appears, but also somewhere else, hidden by the geometry of space-time. We are living inside a lens crafted by gravity, and every glimpse we take is filtered through it. What we call reality is not raw, but refracted. Yet this does not lessen the wonder. It deepens it, reminding us that our perception is not separate from the forces that create the cosmos. The dance of curved space is therefore not just a scientific fact, but a poetic truth. Light is the storyteller, carrying tales from across time, but gravity choreographs its path, bending it, delaying it, and sometimes magnifying it for our eyes. Together they perform a ballet that has lasted since the dawn of the cosmos. And the more carefully we watch, the more of their steps we discern. we begin to realize that the universe is not simply observed but interpreted, its meaning shaped by the very forces that make it possible for us to see. Yet even this grandeur is not the final word. For there are places where the dance becomes so intense that light can no longer escape. These are the realms of black holes, the ultimate stages where gravity leads and light can only follow to its end. To journey further into the partnership of these cosmic architects, we must venture to the edges of those horizons, where the dance of curved space turns into a drama of light's defeat. The dance of curved space reaches its most breathtaking form when entire clusters of galaxies, each one a city of stars, bend the light that passes through them. These clusters are among the most massive objects in the cosmos, their combined gravity creating wells so deep that light from background galaxies is drawn into sweeping arcs and shimmering halos. To gaze upon such a scene is to witness space-time itself acting as an artist, painting illusions in the sky. The galaxies in the foreground are not aware of their role, and the distant galaxies being magnified have no say in how their light is displayed. Yet together, under the choreography of gravity, they perform a spectacle that allows us to see farther than any human technology alone could achieve. This phenomenon is not rare. The universe is filled with distortions. Weak lensing, where light is bent only slightly, affects nearly every photon that travels across great distances. Strong lensing, where arcs and rings are obvious to the eye, occurs in the densest regions. Both are governed by the same principle, the same geometry. When we study these effects, we are not only learning about the galaxies whose light is bent, but also about the invisible structures that bend them. In this way, the dance of curved space doubles as a cosmic map. It lets us trace the outlines of dark matter, which neither glows nor reflects, but still exerts its relentless pull. Consider the case of the Hubble Space Telescope, which has captured some of the most extraordinary examples of this phenomenon. In its images, we see galaxies multiplied, smeared into arcs, or arranged in rings so precise that they look designed. Yet these are not artifices, but revelations. They show us galaxies that would otherwise be too faint to detect, their ancient light amplified by cosmic geometry. In some cases, we are looking at galaxies as they were when the universe was only a fraction of its current age. Gravity has not only bent their light but has delivered their stories across billions of years, placing them within our reach. The precision with which light responds to gravity is absolute. Every photon follows the same rules, whether it left a star in our neighborhood or a galaxy on the far side of the cosmos. This constancy allows us to test the very foundations of relativity. We measure the angles of bending, the delays of arrival, and the shifts in frequency, and we find them always in agreement with Einstein's predictions. The universe is not only elegant, but consistent. The dance is precise. And through that precision, we find truth. It is almost paradoxical that we learn most about the invisible through the visible. Light, which is the only messenger we can see directly, becomes our translator for gravity, which is otherwise silent. We cannot touch space-time or hear it with our senses, but we can observe how light moves through it. In doing so, we glimpse the shape of the unseen. This is why astronomers sometimes describe light as the language of the universe. Without it, gravity's sculpting hand would remain hidden. With it, the curves of space become legible. The cosmos speaks to us in photons guided by invisible pathways. Our daily experience is a quiet echo of this truth. The signals that guide ships across oceans, the broadcasts that circle Earth, the timing of financial networks, all rely on light traveling through curved space. The corrections required are tiny, but they are real, and without them the systems would unravel. We live in the age where the predictions of curved space are no longer only grand theories tested during rare eclipses. They are practical necessities, as vital to modern life as electricity or air travel. The dance of curved space is not confined to distant galaxies. It is woven into the fabric of our civilization. Yet the greatest marvel is not what we gain from this knowledge, but what it suggests. If light can be bent, magnified, delayed, and stretched, then the universe itself is a living lens. Every view we take of the cosmos is both a direct sight and a distortion. What we think of as reality is a tapestry shaped by invisible hands. Our place in it is therefore not as detached observers, but as participants. moving within the same curved stage that guides every beam of light. This realization binds us more closely to the cosmos. We are not looking at something separate, but at the same dance of which we are a part. And so the journey continues. The bending of light around stars and galaxies shows us the grace of curved space, but there are places where this dance becomes so fierce that light cannot emerge at all. There are horizons where even photons surrender, where gravity closes its hand around them. To follow the story of light and gravity further, we must descend toward those ultimate stages, the realms of black holes, where the cosmic architects reveal their most dramatic designs. The bending of light by gravity is more than a subtle distortion. It is a gift that the universe offers, a natural telescope that allows us to peer farther than any machine we can build. When Einstein first described how light would follow the curvature of space, he could hardly have imagined that future astronomers would use this principle to map galaxies invisible to even the largest observatories. And yet, here we are, using gravity itself as a lens to magnify the distant past. In its simplest form, gravitational lensing occurs when a massive object like a galaxy cluster lies between us and a more distant galaxy. The light from that faraway source is forced to bend around the cluster, reaching us along multiple paths. To our eyes, or to our cameras, the background galaxy may appear stretched into arcs, doubled into twin images, or wrapped into a complete circle known as an Einstein ring. These illusions are not coincidences. They are precise reflections of the underlying geometry, written across the sky like signatures of curved space-time. Each distorted arc is a message from the past, delivered only because gravity reshaped its journey. Strong lensing is the most dramatic example. In some cases, a single quasar, a brilliant beacon, powered by a black hole, billions of light years away, can appear as 4 or even 5 separate images around a foreground galaxy. Astronomers call these Einstein crosses, and they are among the most striking sights in the heavens. Yet even more subtle is weak lensing, where the shapes of background galaxies are shifted only slightly, by less than 1%. By gathering images of millions of such galaxies, scientists build statistical maps of the invisible matter in between. It is like watching ripples on the surface of a pond to deduce the stones hidden beneath. This ability to map the unseen is crucial because most of the matter in the universe does not shine. Dark matter outweighs the stars and gas we can see by a factor of 5. It cannot be detected directly with any telescope, but its gravity bends light, and that bending betrays its presence. By studying the distortions of distant galaxies, astronomers have traced the distribution of dark matter into filaments and webs, stretching across billions of light years. These cosmic structures are the scaffolding upon which galaxies form, and without gravitational lensing, we would never have glimpsed them. Light, guided by gravity, exposes what would otherwise remain hidden. The power of this natural telescope is astonishing. In 2014, the Hubble Space Telescope captured an image known as the Hubble Frontier Fields, where a massive cluster magnified galaxies more than 10 billion light-years away. Some of these galaxies were seen as they were only a few 100 million years after the Big Bang, at the dawn of cosmic history. Without lensing, they would have been invisible, too faint to register. With it, they became clear, allowing us to study how the first generations of stars assembled and ignited. Gravity had not only sculpted their structures, but also granted us the chance to witness them. But lensing is not only a window into the past, it is also a tool for measuring the expansion of the universe itself. When light from a distant quasar travels along different bent paths around a galaxy, the images arrive at different times. The delays, measured in days or even weeks, depend on both the geometry of the lens and the rate of cosmic expansion. By carefully studying these time delays, astronomers can estimate the Hubble constant, the number that tells us how fast the universe is stretching. In this way, gravitational lensing is not only a magnifier, but also a clock, ticking with the rhythm of curved space. The beauty of lensing lies in its inevitability. It happens whenever light encounters mass. Whether we are watching stars bend during an eclipse, galaxies magnify one another, or clusters stretch the glow of the early universe. It is a reminder that the cosmos is not static but alive with interactions. Every photon you see has likely been bent at least once along its journey. The universe itself is a hall of mirrors, and we are deciphering its reflections. This natural telescope is not perfect. Its images are warped and stretched, sometimes confusing and chaotic. But within that chaos lies knowledge. By modeling the distribution of matter in the lens, astronomers can reconstruct the original shape of the background source. In doing so, they create a view sharper than any single telescope could provide. Nature itself assists us, lending its gravity to extend our vision. It is as though the cosmos wants to be seen, offering us glimpses of its distant past through the very forces that shape its present. And yet, as remarkable as lensing is, there are limits. If the mass grows too dense, if the curvature becomes too steep, then light is no longer bent into useful paths. It is trapped instead, unable to return. At that boundary, the lens becomes a prison, and light disappears from the stage. To follow the story further, we must turn to those places where even photons cannot escape. The mysterious realms of black holes, where gravity's dominance over light is complete. The universe is filled with illusions crafted by gravity, and among them, gravitational lensing is one of the most profound. When light from a distant galaxy begins its journey, it does not know that billions of years later, it will encounter a massive cluster lying in its path. To the photon, there is no choice. It simply follows the straightest possible line. Yet, in curved space-time, that straight line is bent. The result is that a single galaxy can appear to us as many. Sometimes it is stretched into long arcs that resemble brushstrokes across the sky. Other times, it is multiplied into distinct images, each one a version of the same object, arriving at slightly different times. What we see is both real and distorted, a reflection of two truths at once: the distant galaxy and the invisible mass that bends its light. Strong lensing occurs when the alignment is nearly perfect and the intervening mass is concentrated. The images produced can be spectacular, such as Einstein rings where light is wrapped into a nearly complete circle around a galaxy. To see one of these rings is to witness the geometry of space itself. The light is not moving in a circle, but because it arrives to us along many bent paths, it appears so. This phenomenon was once considered exotic, yet modern surveys find them frequently, each one a confirmation that the laws of relativity are written across the sky. These rings and arcs are more than curiosities. They magnify faint galaxies lying far behind the lens, acting like cosmic magnifying glasses that let us glimpse structures we could not otherwise reach. Weak lensing, by contrast, is more subtle, but no less important. Every background galaxy we see has had its light slightly sheared and stretched by the combined pull of all the matter along its path. To the naked eye, this distortion is imperceptible. But by analyzing millions of galaxies across wide swaths of the sky, astronomers detect a statistical pattern in their orientations. The effect is like watching a field of grass swaying in the wind. The individual blades may appear random, but together they reveal the direction of the invisible breeze. In the same way, weak lensing reveals the invisible presence of dark matter, the hidden substance that dominates the mass of the cosmos. Through weak lensing, scientists have mapped the universe on scales unimaginable to earlier generations. They have traced the cosmic web, a vast network of filaments and knots that stretches for billions of light years. Within those filaments lie clusters of galaxies, bound together by dark matter's gravity. Without lensing, this structure would remain a theory. With it, we see the skeleton of the universe itself. The visible galaxies are only the lanterns hung along the filaments. The true architecture is dark, yet it shapes everything. Light, bent and distorted, carries the imprint of this architecture across the cosmos to our telescopes. These maps not only confirm the existence of dark matter, but also test our understanding of cosmic expansion. By measuring how weak lensing evolves with distance, astronomers probe how structures grow over time. If gravity was stronger or weaker than we believe, or if dark energy behaved differently, the patterns would not match. Yet so far, the observations align with predictions. The cosmos is consistent, though mysteries remain. The exact nature of dark matter is still unknown, and lensing continues to sharpen our questions even as it answers others. Gravitational lensing has also become a tool for discovery. Some of the most distant galaxies known were first spotted because their light was magnified by clusters, acting as giant lenses. In some cases, Astronomers have observed individual stars at cosmological distances, normally far too faint to detect, revealed for a brief moment when a lensing event amplified their light. These stellar beacons allow us to study the early generations of stars, those that lived and died long before our sun was born. Without the aid of gravitational lensing, such windows into the young universe would remain closed. This natural magnification has another gift. It allows us to see how light and time themselves are stretched. When a quasar's light is split into multiple images by lensing, each image follows a different path. Because those paths differ in length and in the depth of gravitational wells they traverse, the light arrives at different times. If the quasar brightens, the flicker appears first in one image, then later in the others. These time delays are not random. They are clocks written into the geometry of space-time. By measuring them, astronomers infer distances and expansion rates, turning gravitational lensing into a ruler for the cosmos. The wonder of this is not only in its utility, but in its beauty. Each lensed image is a painting made by the universe itself. No artist could design arcs that span galaxies or rings that shine like celestial halos. These are the brushstrokes of gravity, illuminated by light. They remind us that the cosmos is not only comprehensible, but also aesthetic, its laws producing patterns that stir both intellect and imagination. Yet lensing also hints at limits. If gravity can magnify and split light, it can also capture it. There exist regions where the bending grows so extreme that no path leads outward. Beyond those horizons, light itself is imprisoned. To follow the story of gravity and light further, we must turn our eyes to black holes, where gravitational lensing ceases to reveal and begins to conceal. The light of distant galaxies does not travel alone. Every step of its journey is guided by the invisible scaffolding of the cosmos, a framework made of dark matter and glowing clusters of galaxies. Gravitational lensing reveals this truth in ways no other method can. When we observe the sky, we are not only seeing the galaxies themselves, but also the distortions their light has suffered along the way. Each arc and smear is a signature written by gravity, a signpost pointing to structures otherwise hidden. Astronomers have learned to treat these distortions as data. By carefully modeling the shape and brightness of lensed galaxies, they reconstruct both the properties of the background source and the mass distribution of the lensing object. This is how we know, with confidence, that dark matter outweighs normal matter 5-1. It is not a guess born of theory, but a measurement derived from light itself, bent and stretched by gravity's hand. In some cases, the models are so precise that they allow us to see galaxies more than 13 billion light-years away, magnified many times over. Lensing turns the universe into a machine for time travel, showing us galaxies as they were at the dawn of cosmic history. But lensing also brings challenges. The very distortions that reveal hidden mass can make it difficult to interpret what we see. Galaxies that appear stretched into elegant arcs must be mathematically untangled, their true shapes reconstructed. This process requires computers, simulations, and careful cross-checks. Yet the effort is worthwhile, because each successful reconstruction provides two rewards: the original view of the background galaxy and the mass map of the lensing cluster. In one stroke, we learn about both the seen and the unseen. The phenomenon also connects to time in unexpected ways. When a quasar's light is split into multiple images, each image may reach us days, weeks, or even years apart. This staggering of arrival times allows astronomers to test the expansion of the universe with extraordinary precision. By comparing the delays with the predicted geometry, they measure the Hubble constant. This method is independent of other techniques, offering a powerful cross-check in one of cosmology's most important debates. Gravitational lensing is therefore not only a window into the past, but a ruler and a clock for the universe itself. The poetry of lensing is inescapable. We are watching the universe reveal itself with its own tools. Gravity sculpts the matter that bends space-time. Light carries the evidence across billions of years. We, on a small world circling a modest star, catch those photons and decipher their story. In this sense, gravitational lensing is not only nature's telescope, but also nature's testament. It tells us that the laws of physics are consistent across the cosmos. that what Einstein wrote a century ago still describes the journeys of photons that began long before Earth even existed. And yet, the story has a darker side. Lensing shows us what happens when gravity grows overwhelming. Arcs and rings delight us, but they also hint at horizons where light cannot escape at all. If curved space can bend light into circles, then with enough mass, it can close those circles entirely, trapping photons forever. To understand this, we must turn from lenses to prisons, from magnifiers to voids. We must look at black holes, where the dance of curved space becomes absolute, and where light, the messenger of the universe, finally falls silent. There are places in the universe where the partnership of gravity and light reaches its breaking point. Here, gravity no longer bends light gently or magnifies distant galaxies. Instead, it becomes an overwhelming prison, drawing everything inward with such intensity that no path leads back out. These are the realms of black holes, objects so extreme that they defy common sense and challenge the boundaries of physics itself. A black hole is born when matter is compressed beyond the ability of light to escape. In a massive star, fusion resists collapse for millions or billions of years. But when the fuel runs out, the balance fails. Gravity crushes the core, and if the mass is great enough, no known force can halt the implosion. The density rises without limit, and space-time curves so steeply that all paths point inward. The event horizon forms, the ultimate boundary. From the outside, it is invisible, marked only by the absence of returning light. Anything crossing it, whether matter, radiation, or information, is lost to the outside universe. Yet the story does not end at silence. Black holes reveal themselves precisely because of their relationship with light. As matter spirals inward, it forms an accretion disk, heating to millions of degrees as friction tears atoms apart. The disk shines brighter than entire galaxies, releasing X-rays and gamma rays that we detect across the cosmos. Light cannot escape the horizon, but the final screams of matter falling toward it blaze brilliantly, announcing the black hole's presence. The paradox is striking. The darkest objects in the universe are also among the brightest sources of radiation. At the edge of these objects lies another wonder, the photon sphere. This is the region where light itself can orbit a black hole, trapped in circles by the extreme curvature of space-time. To an outside observer, photons circling this sphere can escape after multiple loops, producing a glowing halo that outlines the darkness within. The size of the photon sphere depends on the mass of the black hole, but its existence is universal. It is a place where light, the fastest traveler in the cosmos, no longer moves freely, but is caught in a perpetual dance around a gravitational abyss. Gravitational redshift deepens the strangeness. Photons climbing away from a black hole lose energy, stretching into longer wavelengths. To us, the light appears dimmer and redder the closer it originates to the horizon. As an object falls in, its signals grow fainter and slower until they vanish altogether, frozen at the edge in our perception. The infalling matter does not appear to cross the horizon from our point of view, though in its own frame, it plunges through without pause. This discrepancy shows the relativity of time itself. Gravity and light conspire to create two perspectives, both valid, yet irreconcilable. For decades, black holes remained theoretical, their existence debated, but evidence grew inexorably. Stars in our galaxy's center orbit at immense speeds around an invisible mass, more than 4 million times that of the Sunday. Their paths reveal what our eyes cannot, a supermassive black hole anchoring the Milky Way. In distant galaxies, jets of plasma stretch thousands of light-years, powered by matter spiraling into black holes, millions or billions of times the mass of the Sunday. And in 2019, the Event Horizon Telescope unveiled the first direct image of such an object, the black hole in galaxy M87. What we saw was not the hole itself, but the glowing ring of light bent around the photon sphere. It was a portrait of the unseeable, made possible only because light and gravity reveal each other even in their fiercest contest. Black holes are not merely curiosities. They are laboratories where physics is tested to its limits. Near them, space-time is warped to extremes, and light behaves in ways impossible elsewhere. they raise questions that remain unanswered. What happens at the singularity, where density becomes infinite? Can information truly be lost, or does it find some path back through quantum processes we do not yet understand? These mysteries connect gravity with quantum theory, two great pillars of science still awaiting reconciliation. And yet, for all their strangeness, black holes are also natural. They are born from stars, shaped by the same forces that govern galaxies and clusters. Their presence is not rare but common. Every large galaxy harbors a supermassive black hole at its core, its mass linked to the growth of the surrounding stars. Their influence is not confined to swallowing light but extends outward, regulating star formation and shaping the fates of entire galaxies. They are both destroyers and creators, balancing the processes of cosmic evolution. To study black holes is to confront the deepest partnership of gravity and light, where one silences the other and yet also reveals itself through that silence. The cosmos hides its most secret places behind horizons, but it also provides us with clues, halos, flares, and shadows that let us glimpse the edges of the abyss. To journey further, we must follow those clues, tracing the ways in which light carries the story of black holes, even as it succumbs to gravity's final command. The existence of black holes challenges not only our imagination, but also our sense of time. Near their horizons, the very ticking of the universe slows. Imagine a spacecraft approaching such a region. To the travelers inside, their clocks run as usual. Seconds pass, minutes pass, their conversations flow without interruption. Yet to an observer watching from far away, those same seconds stretch longer and longer. The signals from the ship grow faint and red, the intervals between them expanding until the vessel appears to freeze at the edge of the event horizon. Light, our cosmic messenger, tells two different stories depending on where it is observed. This is not illusion, but reality. Time itself is bent by gravity, and light carries the proof. The photon sphere offers an even stranger theater. Here, photons are trapped in unstable orbits, circling the black hole at the speed of light. A single photon may loop once, twice, or many times before escaping outward. To a telescope, these looping photons create multiple stacked images of the universe behind the black hole. Echoes upon echoes fading into infinity. In principle, one could see an endless sequence of copies of the same star field, each dimmer and closer to the horizon than the last. In practice, the images blur together, but the effect is real. Light becomes both prisoner and messenger, weaving ghostly repetitions that tell us about the geometry of curved space. When astronomers turned the Event Horizon Telescope toward Galaxy M87, they captured this spectacle. The image revealed a luminous ring encircling a dark shadow, the boundary defined by the photon sphere and the event horizon. It was not a photograph in the ordinary sense, but a reconstruction built from radio waves gathered by observatories across the Earth. Still, it was light that made the image possible. Photons bent around the black hole, delayed and redshifted, finally reached us after 55 million years, only to be caught by instruments designed to test a century-old theory. The agreement with Einstein's predictions was extraordinary. The ring's size and shape matched what relativity demanded. The dance of gravity and light had been captured, and the world saw it for the first time. This triumph was more than scientific. It was cultural, a moment when humanity collectively glimpsed something once thought unseeable. The dark heart of a galaxy became visible, not by shining light of its own, but by the way it bent the light of the matter surrounding it. The image confirmed what theory and indirect evidence had long suggested, that black holes are not mere abstractions, but real, tangible objects in the universe. Their shadows are as much a part of the cosmos as the stars and galaxies themselves. Supermassive black holes are not isolated curiosities. They shape the evolution of their galaxies. As matter falls inward, it does not all vanish silently. Some of it is channeled into colossal jets, streams of plasma moving near the speed of light and stretching across intergalactic space. These jets can regulate star formation, heating the gas in galaxies and preventing it from collapsing into new stars. In this way, the darkest objects become agents of creation, influencing when and where galaxies grow. Gravity's most extreme expression thus becomes a sculptor of cosmic history, and light once again carries the evidence, blazing outward in radio waves and X-rays that span millions of light years. Our own galaxy harbors such a presence. At its center lies Sagittarius A star, a supermassive black hole with a mass 4 million times that of the Sunday. Stars orbit this unseen object at speeds of thousands of kilometers per second, tracing perfect ellipses around an invisible anchor. Decades of observations have confirmed its mass with breathtaking accuracy. Recently, the Event Horizon Telescope turned its gaze here as well, revealing a ring of light similar to that of M87, though blurred by the gas and dust in our galactic core. To look upon this image is to realize that we live in a galaxy dominated by a shadow, a silent colossus that has shaped our history from the beginning. Yet for all we have learned, mysteries remain. At the core of every black hole lies the singularity, a point where our current understanding fails. Here, density rises beyond measure, and space-time curvature becomes infinite. The laws of physics, as we know them, break down. Light cannot reach us from this realm, and gravity's grip prevents us from sending probes to investigate. We stand at the edge of knowledge, with theory suggesting possibilities, but no observations to confirm them. Some ideas point to quantum effects that could soften the singularity. Others suggest that information may escape in ways we do not yet grasp, through faint radiation predicted by Stephen Hawking. Whatever the truth, it is clear that black holes sit at the crossroads of relativity and quantum mechanics, demanding a new synthesis we have yet to achieve. What makes these enigmas so powerful is that light remains our only guide. Even as photons are bent, delayed, and redshifted, they carry the signatures of the processes unfolding near the horizon. Every flicker of X-rays, every burst of radio waves, every distorted image provides clues. Gravity may silence light beyond the horizon, but at the threshold, it forces light to shout with a brilliance unmatched anywhere else in the universe. To study black holes is to listen to those shouts, to read the last words of matter as it succumbs, and to interpret the story gravity forces light to tell. As we push further, we realize that black holes are not merely exotic objects, but essential characters in the cosmic narrative. They show us what happens when light fails, when gravity becomes absolute, and in that failure lies revelation. The absence of light is not emptiness, but a canvas upon which the universe writes its deepest truths. To continue this journey, we must explore how black holes not only conceal, but also expose, how their shadows are windows into the workings of space-time itself. At the edge of black holes, light performs its most haunting role. It becomes stretched into infinity, redshifted, until its frequency vanishes beyond our ability to detect. This is gravitational redshift at its extreme, the fading of photons as they climb out of a pit too deep to escape. From a distance, infalling matter seems to slow, frozen in time just outside the event horizon. In truth, the matter continues inward, but the light it emits grows weaker and slower until it disappears. What we witness is not the fall itself, but the story light can no longer tell. Gravity edits the script, erasing the final chapter from our view. This interplay makes black holes not only objects of fascination, but laboratories for fundamental physics. Near their horizons, the rules of relativity and quantum theory collide. Stephen Hawking predicted that black holes are not entirely black. Quantum fluctuations at the edge can produce pairs of particles, with one falling inward and the other escaping. The result is a faint emission now known as Hawking radiation. Over unimaginable spans of time, this process would cause black holes to evaporate, returning their mass to the universe as radiation. If true, this means that light has the last word, whispering the story of black holes even after gravity seems to have silenced it. The implications are staggering. If information can escape in this way, then black holes may not destroy knowledge after all. Instead, they may transform it, encoding it in subtle patterns of radiation. This is the heart of the information paradox, a puzzle that has driven physicists for decades. Does gravity truly erase the past, or does light preserve it in forms we do not yet understand? The answer would not only deepen our grasp of black holes, but also bring us closer to uniting relativity with quantum mechanics. Our instruments continue to search for evidence. Telescopes tuned to X-rays and radio waves watch the skies for flares near event horizons. Gravitational wave detectors listen for the ripples in space-time produced when black holes collide, carrying signatures of their masses and spins. Each observation is a piece of the puzzle, a clue written in the joint language of gravity and light. Together they describe a universe where the most violent events become messages, where destruction itself becomes revelation. For all their mystery, black holes are woven into the fabric of cosmic history. Without them, galaxies would not grow as they do. Their influence shapes the distribution of stars, regulates the birth of new systems, and may even seed the conditions for life by stirring and heating the material from which planets form. Far from being rare anomalies, black holes are central to the story of structure and evolution. They are as much a part of the universe as the stars, though their role is to hold shadows rather than shine. And yet, for all their power, they remain dependent on light to tell their story. We know them not by direct vision, but by the way they bend, trap, and distort photons. We measure their masses by watching the stars that orbit them. We map their silhouettes by capturing the glow of gas spiraling to its doom. Even Hawking radiation, if ever detected, would be a final testament carried by light. Gravity may dominate, but without light, its rule would remain invisible. The lesson of black holes is therefore twofold. They show us the ultimate victory of gravity, where even light cannot escape. But they also show us the resilience of light, which continues to reveal, to narrate, to carry information, even at the threshold of silence. This partnership, fierce and paradoxical, defines the frontier of physics. It teaches us that absence can be presence, that darkness can be revelation, and that the universe hides its deepest truths in the interplay between what falls and what shines. To move forward, we must follow this partnership beyond black holes, to the way gravity and light together define time itself. For every clock we build, every photon we measure, is subject to their influence. The tick of the universe is written in light, and gravity decides how that tick is heard. Beyond the shadows of black holes lies another truth, one that touches not only the cosmos, but every moment of our lives. Time is the rhythm of the universe, yet it is not absolute. We often imagine it as steady, a cosmic metronome ticking at the same pace everywhere. But Einstein revealed that time is elastic, shaped by both motion and gravity. And once again, light is the messenger that tells us how this works. Every clock we build, from the simplest pendulum to the most precise atomic device, is ultimately synchronized with light. The oscillations of photons define our standard of seconds, and through them, we measure the passage of time. Gravity, however, alters that rhythm, stretching or compressing the intervals between ticks depending on where the clock rests. This becomes most clear when we compare clocks at different altitudes. On a mountain, where Earth's gravity is weaker, an atomic clock ticks slightly faster than one at sea level. The difference is minuscule fractions of a billionth of a second, but it is real, and modern instruments can measure it with ease. This effect, called gravitational time dilation, shows that time is not universal. It flows differently depending on the curvature of space-time. Photons, emitted by atoms, carry this truth. Their frequencies shift depending on the strength of the gravitational field, a phenomenon known as gravitational redshift. Light, in its steady oscillations, exposes the malleability of time itself. The first direct demonstration of this came in the 1960s. Two physicists, Robert Pound and Glenn Rebka, performed an experiment in a Harvard tower. They measured the frequency of gamma rays emitted at the bottom and received at the top, a difference of only 22 meters. Even across this short height, they detected the redshift predicted by Einstein's theory. Light climbing against gravity lost energy, and its frequency decreased. The experiment was a triumph, proving that time and light are intertwined even on human scales. Decades later, satellites made the effect undeniable. The Global Positioning System relies on a constellation of orbiting clocks, transmitting signals to Earth. Without correcting for gravitational time dilation, those clocks would drift apart from their ground-based counterparts, leading to errors of kilometers in navigation each day. Instead, engineers incorporate relativity into their designs, adjusting the frequencies of the satellite's signals to align with those on Earth. Each time your phone locates you on a map, it does so by trusting Einstein's insights. by acknowledging that light and gravity together shape the beat of time. The consequences extend far beyond technology. In the vicinity of massive objects, the distortion of time becomes dramatic. Near a neutron star, where gravity is billions of times stronger than on Earth, a second for an outside observer may stretch into hours for someone hovering near its surface. Near the horizon of a black hole, the difference grows infinite. To us, an object falling toward the horizon appears to slow and freeze, its signals stretched endlessly. For the object itself, time flows normally until the instant it crosses into darkness. These paradoxical perspectives coexist, reconciled only by the relativity of time. And once again, light is the messenger carrying both stories, its redshift and delay, encoding the truth of gravity's grip. The fact that light defines time also means that our understanding of the cosmos is bounded by it. When we speak of the age of the universe, about 13.8 billion years, we are measuring in units defined by photons. We use the steady oscillations of atomic transitions, calibrated by light, to keep our clocks. We then compare those rhythms with the signals from distant galaxies, their redshifted light telling us how long they have traveled. Time, in cosmology, is always measured by light, and gravity, by bending and stretching that light, becomes the editor of cosmic history, altering the tempo of the universe's unfolding. Every photon is therefore a timekeeper. Its wavelength and frequency reveal the gravitational fields it has traversed. By analyzing spectra from stars and galaxies, we read not only their composition and motion, but also the curvature of space-time in their vicinity. Light is both the message and the clock that times its own delivery. This dual role makes it the most faithful witness of the universe's events. Where matter can be destroyed or altered, photons travel unscathed across billions of years, carrying with them the imprint of the time and place they left. The elegance of this truth is that it connects the vast with the intimate. The same principles that govern redshifted photons escaping the surface of a neutron star also govern the timing of your phone's GPS signal. The same equations that describe the slowing of time near a black hole also describe the difference between clocks at the top and bottom of a building. Gravity and light do not separate the cosmic from the personal. They link them, showing that the universe is one continuum where the ticking of time is always relative, always shaped by the interplay of curvature and oscillation. And so we begin to see that time itself is not a neutral backdrop, but a phenomenon created by gravity and revealed by light. Every tick of every clock is a local truth, valid in its own frame, but different from every other. The cosmos does not march to a single beat. It pulses with countless rhythms, each one shaped by space-time and carried by photons. To explore this more deeply, we must follow light into the most extreme laboratories of time, where gravity warps seconds into years, and where clocks become windows into the structure of reality itself. Time is not merely a backdrop against which the universe unfolds. It is an active player, reshaped by gravity and revealed by light. To grasp this truth, scientists have performed experiments both on Earth and in space, each one confirming that time runs differently depending on where you stand in the cosmic landscape. One of the earliest demonstrations came from flying atomic clocks aboard airplanes. In 1971, physicists Joseph Huffley and Richard Keating carried precise cesium clocks around the world, once eastward and once westward. When the clocks were compared with those left at the United States Naval Observatory, the differences matched Einstein's predictions. Those moving eastward, in the same direction as Earth's rotation, lost time relative to the ground clocks, while those moving westward gained time. The combined effects of motion and gravity had altered the passage of time itself, with light's oscillations serving as the judge. Later, rockets and satellites extended the tests further. Atomic clocks launched into orbit tick faster than those on Earth's surface because they are farther from Earth's mass and feel weaker gravity. The difference is small tens of microseconds per day, but without correcting for it, the timing of satellite signals would drift rapidly out of sync. Engineers now adjust the frequency of these orbiting clocks before launch, so that once they reach orbit, they align with those on the ground. Every successful navigation, every synchrony between global networks, depends on this careful acknowledgement that gravity stretches the pace of time, and that light tells us how much. On Earth, even more refined experiments use lasers to measure the difference in time dilation over mere centimeters. Two atomic clocks placed at different heights in the same laboratory tick at slightly different rates, measurable because light from one to the other carries the shift in frequency. This proves that gravity's influence on time is not confined to stars or black holes, but exists everywhere, even in the span of a human hand. Time is not an absolute river flowing smoothly across the cosmos. It is a field, warped and sculpted by mass, its rhythm defined by the photons we use to measure it. This revelation changes the way we think about the universe. When we look at distant galaxies, we are not only seeing them as they were billions of years ago, but also measuring how time flowed differently in their gravitational environments. The light that reaches us has been stretched not only by cosmic expansion, but also by the wells of gravity it escaped. Each photon is a messenger carrying two layers of history: the moment it was born and the story of the terrain it crossed. By analyzing spectra, astronomers decode this history, reading time itself from the lines etched into the starlight. The implications reach into the deepest questions of physics. If time is elastic, then what we call the age of the universe is not a single number experienced everywhere equally. It is an integration of countless local times, each shaped by gravity. The cosmos is not a single ticking clock, but a symphony of rhythms, all connected by light. Our instruments simply translate those rhythms into a shared language, allowing us to speak of seconds and years as if they were universal, even though the universe itself does not obey such absolutes. The wonder is that we can use this knowledge not only to navigate space, but to test the very laws of nature. Experiments with gravitational redshift and time dilation provide some of the most precise confirmations of general relativity. Each photon observed, each clock compared, strengthens our confidence that the universe is indeed governed by these elegant rules. And yet, we also know that relativity must one day be joined with quantum mechanics, and that black holes and the Big Bang hold secrets we cannot yet reconcile. Here again, light as a cosmic clock may guide us, hinting at the pathways toward a deeper theory. The partnership of gravity and light therefore defines not just space but time itself. To understand one is to understand the other. Every tick of a clock is really the oscillation of light, and every oscillation is altered by the curvature of space-time. In this way, light is more than illumination. It is the heartbeat of the cosmos, and gravity is the hand that changes its tempo. But the story does not end with laboratory experiments or satellite systems. On cosmic scales, the stretching of time by gravity shapes how stars evolve, how galaxies form, and how the universe itself unfolds. To follow the trail further, we must examine how the interplay of light and gravity reveals not only the visible, but also the invisible, exposing the structures of dark matter and the strange influence of dark energy that drives the expansion of space. The clocks we build on Earth and launch into orbit are fragile instruments compared to the vast timekeepers of the cosmos. Stars themselves measure time, burning their fuel in predictable rhythms set by mass and gravity. The light they emit tells us how long they have lived, how quickly they burn, and when they will end. A massive star exhausts its fuel in only a few million years, while a small red dwarf may burn quietly for trillions. Gravity dictates the pressure inside each star, and light carries the result outward across space. In this way, stars are natural clocks, their pulses and brightness encoding the ages of galaxies. On even larger scales, the cosmos itself is a clock wound by the Big Bang. The cosmic microwave background, that faint glow released when the universe was still a newborn, is a frozen moment in time. Its photons have been stretched by billions of years of expansion, redshifted into microwaves that wash across us today. By measuring their patterns, we read the age of the universe like geologists reading tree rings. Gravity has shaped those patterns, while light has preserved them, giving us a time capsule from nearly 14 billion years ago. No other messenger could have survived that journey. Light alone acts as the recorder, carrying the story of the universe's childhood into the present. Even phenomena as violent as supernovae and gamma-ray bursts serve as cosmic clocks. These events are brief, lasting seconds to months, yet their timing provides distance scales and tests of relativity. When light from a supernova reaches us, We can measure how its brightness changes over time, revealing both the energy of the explosion and the expansion rate of the cosmos. When two neutron stars collide, the light they emit alongside gravitational waves arrives with exquisite synchronization, allowing us to compare the two messengers and test whether they obey the same universal speed. Each observation becomes a clock, its ticks measured in photons, and its rhythm set by gravity. Closer to home, we ourselves are bound to these cosmic rhythms. Every sunrise is a reminder that light defines our days, while Earth's gravity shapes the length of those days by holding our orbit steady. Our biological clocks are tuned to light, synchronized with the turning of our planet. On scales from seconds to eons, we live within the partnership of light and gravity. It is not an abstraction, but the foundation of every moment we experience. The realization that time is flexible, that light encodes its passage, forces us to rethink our place in the universe. We are accustomed to believing in shared moments, in universal nows. Yet relativity tells us that each observer carries their own slice of time, curved by gravity and stretched by motion. What unites these perspectives is light, for it is the only messenger that bridges them. Photons carry the rhythm of clocks from one frame to another, allowing us to compare and communicate across the relative flow of time. Without light, each region of the cosmos would live in isolation, unable to know the tick of any other. This insight has profound consequences. If time is not universal, then history itself is not a single thread, but a tapestry woven from countless strands. Light is the shuttle that carries those strands across the loom, stitching them together into the narrative we perceive. Gravity, meanwhile, stretches and bends the weave, altering its pattern. Together they produce the fabric of reality, where time is both local and shared, both relative and universal in its connection through photons. The story of light as a cosmic clock is therefore not only about measurement, but about meaning. It tells us that the universe is not static, but dynamic, that the flow of time is part of the structure of space-time itself. It shows us that our moments are linked to the stars, that the seconds we count on Earth are related to the pulses of distant quasars and the cooling of the cosmic background. To live in such a universe is to exist within a grand symphony, where gravity conducts and light plays the notes. As we move forward, this symphony will guide us deeper into the mysteries that remain. Light not only measures time, but also illuminates the dark universe, revealing the hidden forces of dark matter and dark energy that shape our fate. To follow the next chapter of this journey, we must let light show us what cannot be seen directly, and let gravity explain why it takes the forms it does. For the cosmos is not only bright but shadowed, and to understand it fully, we must explore how gravity and light together illuminate the dark. The stars and galaxies we see are dazzling, but they are only a fraction of what exists. Most of the universe is hidden, composed of matter and energy that do not shine. Yet we are not blind. Light, bent and stretched by gravity, carries clues about this invisible majority. In this way, the cosmos offers us a paradox. Darkness dominates, but light reveals it. We see the unseen not by direct vision, but by the distortions written into photons on their long journeys to us. The first hint of this hidden universe came from the motions of galaxies. In the 1930s, astronomer Fritz Zwicky studied the Coma Cluster and noticed that galaxies moved too quickly to be held together by the visible mass of stars alone. Something unseen must be providing the extra gravity. Decades later, Vera Rubin confirmed the effect within galaxies, showing that stars on their edges orbited far faster than expected. The luminous matter, the stars, gas and dust, was only a small part of the story. An invisible halo, now called dark matter, had to surround every galaxy. Dark matter does not emit or absorb light, but it bends it. Gravitational lensing allows us to map its distribution directly. When we observe arcs and distortions around clusters, the degree of bending tells us how much mass is present, regardless of whether it glows. Time and again, the measurements reveal halos of invisible matter enveloping galaxies, extending far beyond their luminous cores. Light, the faithful messenger, betrays the presence of what it cannot illuminate directly. Without this tool, dark matter would remain a ghost. With it, We can draw its outline across billions of light years. On even larger scales, the cosmic microwave background provides another map. This faint afterglow, released when the universe was only 380,000 years old, has traveled across space for nearly 14 billion years. Along the way, it has been bent and twisted by the gravity of intervening structures. By measuring these distortions with exquisite precision, satellites like Planck have reconstructed the distribution of matter through time. The result is a cosmic cartography, showing us how dark matter seeded the web of galaxies that fills the universe today. Light from the earliest era has become the surveyor of the dark, but the mystery deepens further. Not only is most of the universe's matter invisible, but most of its energy is hidden as well. Observations of distant supernovae in the 1990s revealed that cosmic expansion is accelerating, driven by something we now call dark energy. Its nature is unknown, but its influence is unmistakable. Galaxies are not merely drifting apart, they are racing away faster and faster. Light again reveals the truth. The redshift of distant supernovae carries the signature of acceleration, showing us that gravity alone cannot explain the cosmos. Some repulsive energy permeates space, pushing it outward. Together, dark matter and dark energy compose 95% of the universe. The stars and galaxies we see account for less than 5%. Yet through light, we can study the whole. Photons, shaped by gravity, act as our translators, turning the invisible into the measurable. Weak lensing surveys map the hidden scaffolding. Supernova light curves measure the accelerating expansion. The cosmic microwave background records the early conditions. Light is the only way we can know the dark universe exists at all. This is perhaps the most astonishing irony of science. What we call darkness is not beyond our reach. Light, when guided by gravity, illuminates it. Every distorted image, every stretched wavelength, every faint whisper from the background carries hints of the unseen. The universe, though mostly dark, cannot hide from the messengers that cross it. The architects of reality ensure that even the invisible is written into the language of photons. Yet, for all we know, mysteries remain. What is dark matter made of? Is it a particle we have yet to discover, or something stranger, perhaps a modification of gravity itself? What is dark energy? Is it a property of space, a field, or something beyond our current theories? Light does not answer directly, but it points the way. The patterns in the sky, the bending of arcs, the rhythm of expansion. These are the clues. The challenge is ours to interpret them. As we press further into this mystery, we see that light is not only an illuminator, but a bridge between epochs. The photons we catch tonight may have left their sources before the Earth even formed. They may have traveled through filaments of dark matter, past clusters shaped by invisible hands, across billions of years of accelerating space. Each one carries the imprint of that journey. By reading it, we transform darkness into knowledge. The dark universe is not a void. It is a structure, an energy, a force shaping everything we see. Without it, galaxies would not have formed, stars would not have ignited, and life would not have emerged. Light shows us this truth, even when it cannot show us the thing itself. Gravity ensures that the unseen still leaves its mark. Together, they turn mystery into map, absence into revelation. And yet, light does more than reveal structures. It also carries echoes from the beginning, whispers of the universe's birth written into its faintest signals. To follow the next step of this story, we must listen to those echoes, comparing them with the ripples of gravity itself, to see how the cosmos speaks in more than one voice. The cosmic microwave background is one of the most delicate gifts the universe has given us, and it is through light that we can read its message. These photons were released when the cosmos was still a child, only 380,000 years old, after matter and radiation decoupled. Before that epoch, light could not travel freely, constantly scattered by the dense plasma that filled space. But when the universe cooled just enough, atoms formed, and photons at last streamed outward. Those same photons are still moving, stretched by billions of years of expansion into faint microwaves that now wash over Earth from every direction. On its own, the cosmic microwave background would appear as a nearly uniform glow. But tiny variations, only a few parts in 100,000, mark the seeds of structure. These are the imprints of primordial density fluctuations, written into light when the universe was young. Gravity later amplified those seeds, gathering matter into filaments, clusters, and galaxies. By studying the subtle patterns in the background, we read the blueprint of cosmic architecture. Light is the archivist, recording the early whispers of gravity's shaping hand. Yet the story does not stop with the release of those photons. Their journey across nearly 14 billion years has been anything but simple. As they moved through the growing structures of the universe, they were bent and lensed by the gravity of dark matter. The result is that the cosmic microwave background we see today is slightly blurred and twisted, carrying the fingerprints of all the intervening mass. By analyzing these distortions, cosmologists create maps of the invisible scaffolding, tracing the distribution of dark matter across time. It is as if the background light is a sheet of tracing paper laid across the universe, its wrinkles revealing what lies beneath. Satellites like WMAP and Planck have measured this background with extraordinary precision. The maps they produced show not only the age of the universe, but also its composition: about 5% normal matter, 25% dark matter, and 70% dark energy. These numbers are not guesses. They come directly from the way photons have been shaped by gravity across cosmic history. Light itself tells us the recipe of reality, even though most of the ingredients remain invisible. On smaller scales, cosmic microwave background lensing provides an even sharper tool. By studying how the background is subtly deflected by galaxy clusters, astronomers weigh the clusters themselves. The amount of bending depends on the total mass, visible and invisible alike. Once again, light reveals what it cannot touch. These measurements confirm that clusters are dominated by dark matter, their visible galaxies only lanterns in a much larger, unseen framework. The same principle extends to dark energy. The accelerated expansion of the universe leaves an imprint on the background by altering how structures grow over time. Photons traveling through regions of varying density lose and gain energy depending on whether the universe is accelerating or decelerating. This effect, called the integrated Sachs-Wolfe effect, shows up as correlations between the cosmic background and large-scale structures. Through these subtle patterns, light reveals the hand of dark energy, a force we cannot see but which dominates cosmic evolution. It is humbling to realize how much of our knowledge rests on these faint signals. The photons of the cosmic microwave background have traveled farther and longer than almost anything else we can observe. They are relics from the dawn of time, and yet they still speak clearly if we listen with the right instruments. By decoding their distortions, we reconstruct the universe's history, from its earliest seconds to its accelerating present. Light, though fragile, carries this burden across billions of years, while gravity ensures that its path records the invisible. These discoveries remind us that darkness is not absence. Dark matter and dark energy are not gaps in our knowledge, but realities written into the very behavior of light. The cosmos cannot conceal them completely because every photon that passes through carries their signatures. When we measure redshifts, distortions, and faint anisotropies, we are listening to the conversation between gravity and light, a dialogue that encodes the hidden majority of the universe. And yet, this dialogue continues in more than one voice. Light is not the only messenger the universe sends us. Gravity itself can ripple across space-time, carrying information in waves that are not blocked or scattered. For most of history, we could see only through light. But now we are beginning to listen to gravity's own music, adding a new dimension to our exploration. To continue the story, we must compare these messengers. Watching how photons and gravitational waves together tell us truths that neither could reveal alone. The revelation that light can unveil the invisible reshapes how we think of the cosmos. For centuries, astronomy was limited to what could be seen directly through telescopes: stars, nebulae, galaxies. But as our instruments grew more sensitive, we discovered that the majority of the universe is not luminous. Dark matter outweighs all the glowing stars 5-1, and dark energy overwhelms them all, shaping the expansion of space itself. The question is not whether these unseen components exist, but how we can continue to study them. The answer once again, is light, guided and transformed by gravity. Weak lensing surveys, which measure the subtle distortions of background galaxies across vast areas of the sky, have become one of our most powerful tools. Each galaxy image is a brushstroke in a larger pattern, and by analyzing millions of them, scientists trace the invisible structures that bend their light. Projects like the Dark Energy Survey and the upcoming Vera Rubin Observatory aim to chart these distortions with unprecedented detail. Their maps will show not only where dark matter lies, but also how it has evolved over billions of years, offering crucial clues to the nature of dark energy as well. Supernovae add another layer of evidence. Type Ia supernovae, stellar explosions of nearly uniform brightness, act as standard candles. By comparing their apparent brightness with their redshift, astronomers measure cosmic distances and the expansion rate. The discovery that these supernovae were dimmer than expected revealed the accelerating universe, the first direct sign of dark energy. Light from dying stars, stretched and reddened by gravity and expansion, became the messenger of a force that shapes the fate of the cosmos. Together, these strands form a tapestry of evidence. Cosmic microwave background distortions reveal the early seeds of structure. Weak lensing maps show the scaffolding of dark matter. Supernova light curves expose the push of dark energy. Each is an independent measure, yet they all converge on the same picture: a universe where the visible is only a small fraction, and the hidden governs the whole. Light, bent and stretched, gives us confidence in what our eyes cannot see. But this illumination is not perfect. The maps are noisy, the measurements subtle, the interpretations uncertain. We stand at the edge of knowledge, guided by light but yearning for more. What exactly is dark matter made of? Is it a particle, a field, or a modification of gravity itself? What is dark energy? Is it a constant property of space or a dynamic force that changes with time? These are not abstract questions. They touch the core of physics, the ultimate fate of the universe, and our understanding of reality. In the coming decades, new observatories will extend our reach. The James Webb Space Telescope is already peering deeper into the past, aided by gravitational lenses that magnify galaxies from the first billion years. The Vera Rubin Observatory will map billions of galaxies, detecting the subtle sway of weak lensing with unparalleled precision. The Euclid mission and NASA's Nancy Grace Roman Telescope will join the effort from space, combining imaging and spectroscopy to untangle the nature of dark energy. Each of these relies on light, but each also depends on gravity's guidance, the distortions that turn darkness into data. It is fitting that light remains our main window into the dark universe. Photons have always been our storytellers, carrying information across space and time. Gravity ensures that those stories contain not just what is bright, but also what is hidden. This partnership has given us a universe where even the unseen cannot remain wholly secret. Darkness leaves traces, and light delivers them to us. Yet, as profound as this is, light is not alone. The cosmos has begun to speak to us in a new language, one we could not hear until recently. In 2015, detectors first caught the ripples of spacetime itself, gravitational waves from merging black holes. For the first time, we were not merely watching light, but listening to gravity directly. The stage of the universe expanded, and its choreography revealed itself in both sight and sound. To move forward, we must bring these messengers together, comparing their voices to build a fuller picture of the cosmos. For most of human history, light was the only messenger we knew. Every observation of the heavens relied on photons, from the faint glow of distant stars to the brilliant flares of supernovae. Light revealed the structure of galaxies, the expansion of the cosmos, and even the presence of the unseen through lensing and redshift. But gravity, though silent in our telescopes, was always there, shaping the very stories light carried. For centuries, we suspected that gravity, too, might send its own signals. Einstein's equations suggested it: ripples in spacetime traveling at the speed of light, produced by massive objects in motion. Yet for 100 years, they remained theoretical, beyond the reach of experiment. That changed in September of 2015, when the Laser Interferometer Gravitational Wave Observatory LIGO recorded a faint, fleeting signal. Two black holes, each more than 30 times the mass of the Sun, had spiraled together over 1 billion light-years away. Their collision sent ripples through space-time that stretched and compressed Earth itself by less than the width of a proton. And yet, after traveling for more than 1 billion years, those ripples were strong enough to be detected by lasers bouncing between mirrors in giant vacuum tubes. For the first time, humanity had heard the universe, not in light, but in gravity's own voice. This discovery marked the dawn of gravitational wave astronomy. Where light could only show us the matter glowing or reflecting, gravitational waves let us sense the motion of mass itself. Black holes, once invisible except for their effects on surrounding matter, now became direct sources of information. Their mergers ring space-time like a struck bell, and the tone carries the story of their masses, spins, and orbits. Light had always been our window, but now gravity opened a door. The cosmos revealed itself in stereo. The differences between light waves and gravity waves are profound. Light can be blocked, absorbed, scattered. A photon may be deflected by dust, bent by gravity, or redshifted by expansion. Its journey is fragile, though long. Gravitational waves, by contrast, pass through matter almost untouched. They travel across the cosmos unimpeded, carrying pristine information about the events that produced them. Where light struggles to escape from deep within stars or black hole mergers, gravity waves race outward, unbound. They give us access to realms light cannot reach, yet their strengths are complementary. Light tells us about surfaces and emissions, the glow of plasma, the arcs of galaxies, the echoes of the Big Bang. Gravitational waves tell us about dynamics, the motion of mass, the rhythm of orbits, the final spirals of collisions. Together, they provide a fuller story. The cosmos is not limited to sight alone. It speaks in multiple voices. And only by listening to both can we understand its song. The detection of gravitational waves also confirmed a central prediction of relativity. Einstein himself had doubted whether such ripples could ever be measured, so small was their effect. The fact that we now detect them regularly, with LIGO and its European partner Virgo, shows not only the power of technology, but the accuracy of theory. Each detection strengthens our confidence that gravity and light together describe the universe with astonishing precision, and each detection expands our horizon, revealing new populations of black holes, neutron stars, and perhaps, in the future, stranger objects still. It is humbling to realize that for billions of years, these signals crossed space unnoticed, shaking Earth subtly with every passing wave. Only now do we have ears sensitive enough to hear them. The universe has always been speaking in gravity as well as light. We are only now learning to listen, and in listening, we discover a cosmos richer, more complex, and more unified than we imagined. But the true power comes when these two messengers arrive together. When gravitational waves and light are observed from the same event, their combined voices reveal far more than either could alone. This is the essence of multi-messenger astronomy. A new era in which the cosmos no longer whispers in isolation, but sings in harmony. When the first black hole mergers were detected, the universe spoke only in gravity. No light accompanied those signals, for black holes colliding in empty space release no photons that can escape. The waves of space-time told us the story of mass and energy, but the sky remained dark. Then, in August of 2017, the cosmos changed its tune. LIGO and Virgo detected a new kind of signal, one lasting longer and rising in pitch like a cosmic chirp. It was the merger of two neutron stars, each about 1.5 times the mass of the Sun, spiraling together in a final dance. For over a minute, their gravitational waves swept across our detectors, revealing details of their orbits and masses. But this time, unlike the silent black hole mergers, there was light. Just 2 seconds after the gravitational waves reached Earth, space telescopes detected a burst of gamma rays from the same region of the sky. Ground-based observatories quickly joined in, and soon astronomers across the globe turned their instruments toward the fading glow. For the first time in history, light and gravity had arrived together from a single cosmic event. The neutron-star collision became one of the most studied phenomena ever observed. A true symphony of multi-messenger astronomy. The combination of signals was transformative. The gravitational waves revealed the masses of the stars, their orbits, and the moment of merger. The light told us what happened afterward. As the stars collided, they produced a kilonova, an explosion powered by the creation of heavy elements. The glow shifted from blue to red over days, showing that gold, platinum, and other rare elements were forged in the fire of the collision. For centuries, we wondered where these elements came from. Now we had the answer, carried by photons born in the wreckage and confirmed by the waves of spacetime itself. The gamma-ray burst added another layer of knowledge. Long suspected to be caused by neutron star mergers, short gamma-ray bursts are among the most energetic events in the universe. By catching one just 2 seconds after the gravitational waves, we confirmed the link. Gravity announced the collision, and light revealed the jet of radiation it launched into space. This synchronization showed that the two messengers obey the same universal speed. Both had traveled over 100 million light-years and arrived almost simultaneously, proving that gravity and light race neck and neck across the cosmos. The aftermath of the collision continued to provide insights. As telescopes followed the fading kilonova for weeks, they traced the production of elements heavier than iron, confirming theories of nucleosynthesis. Radio observations revealed the expanding shockwave plowing into interstellar gas. X-ray telescopes captured the lingering energy of the explosion. Every part of the electromagnetic spectrum contributed, while gravitational waves provided the framework for interpreting the sequence. Together, they painted a picture no single messenger could offer. This event marked the beginning of a new era. For the first time, we could test relativity, nuclear physics, astrophysics, and cosmology all at once. Gravitational waves told us how matter behaves at densities greater than atomic nuclei. Light showed us the chemical enrichment of the universe. The combination allowed us to measure the Hubble constant, comparing gravitational distance scales with redshift from light. The collision of two stars had become a laboratory spanning all of physics. It is hard to overstate the impact of this discovery. The universe revealed not only that it speaks in multiple voices, but also that those voices harmonize. Gravity waves and light are not competitors but companions, carrying different parts of the same story. Each alone would have been remarkable. Together they transformed our understanding of cosmic events. This new way of seeing ensures that the future of astronomy will be richer than its past. We will no longer rely on photons alone, but will listen for the ripples in space-time that accompany them. The cosmos, once mute except for light, now sings in stereo. And we are only beginning to learn the music. But what lies ahead is even greater. As detectors grow more sensitive and telescopes more powerful, we will observe more such symphonies, unlocking mysteries that light alone cannot solve. To see how this dual vision reshapes our place in the cosmos, we must look deeper into the meaning of multi-messenger astronomy, where two messengers together tell one unified story. The success of the neutron star collision of 2017 was not a solitary triumph, but a beginning. It showed what becomes possible when we combine the voices of gravity and light. Since then, astronomers have prepared for a future where every great cosmic event is studied through multiple messengers, each one revealing a layer of truth. This is the birth of multi-messenger astronomy, a field where photons, gravitational waves, neutrinos, and even cosmic rays all play their part. Light remains the most familiar messenger. It tells us about surfaces, temperatures, chemical compositions, and magnetic fields. It arrives in every wavelength, from radio to gamma rays, carrying information about nearly every process in the cosmos. Gravitational waves, in contrast, tell us about the invisible dance of mass. They describe orbits and collisions, ripples in space-time itself. When combined, these two messengers allow us to build a fuller, richer narrative. The gravitational waves reveal the script, while light provides the performance. Already, this partnership has borne fruit. By comparing the arrival times of photons and gravitational waves, we confirmed that both travel at the same speed, strengthening relativity's predictions. By combining the distance measured from gravitational waves with the redshift measured from light, we tested the expansion rate of the universe, offering new clues to the ongoing debate about the Hubble constant. By following the glow of kilonovae alongside the chirps of space-time, we traced the origins of elements that make up planets, jewelry, and even the iron in our blood. The marriage of messengers transforms astrophysics into a symphony of voices, where no single instrument carries the full melody. This approach is not limited to neutron stars. In the coming years, we expect to hear and see black holes merging with neutron stars, tidal disruptions of stars by supermassive black holes, and perhaps signals from processes we cannot yet imagine. Each will provide not just one messenger but several, allowing us to test our theories from multiple directions. Where once we relied only on light, we now stand at the threshold of a multi-dimensional astronomy that listens as well as looks. The philosophical impact is profound. For centuries, humans thought of themselves as creatures of sight, defining the cosmos by what could be seen. Now we realize we are also creatures of hearing, sensitive to the vibrations of space-time itself. The universe is not silent, nor is it limited to light. It sings in ripples and flashes, in waves and particles, in harmonies we are only beginning to perceive. To listen is to acknowledge that reality is richer than our eyes alone can show. Multi-messenger astronomy also expands our sense of unity. Every detection requires a network of instruments scattered across the Earth and in space, cooperating to catch signals that last only seconds or minutes. When gravitational waves sweep through, detectors on different continents record them. When light follows, telescopes worldwide turn to watch. Humanity responds as a single species, working together to hear the cosmos. In this sense, multi-messenger astronomy is not just a scientific advance, but a cultural one, reminding us that we are united by our curiosity and our place in the same universe. As we look ahead, the promise of new instruments grows. Next-generation gravitational wave observatories, like the Einstein Telescope and the Cosmic Explorer, will hear fainter and more distant signals. Space-based detectors like LISA will tune to lower frequencies, catching the slow dances of supermassive black holes. Telescopes across the electromagnetic spectrum will watch in coordination, ready to capture every flash and flare. Together they will weave a tapestry of messages, a chorus of photons and waves. The message is clear. Light and gravity are not rivals but companions. They reveal different aspects of the same reality. Alone, each is powerful. Together, they are transformative. With both, we hear the heartbeat of the universe and see its face at the same time. Multi-messenger astronomy is not merely a new tool. It is a new way of knowing. A recognition that the cosmos speaks in more than one voice. And so the stage is set for the next revelation. Having seen how gravity and light together tell us the stories of collisions and creation, we now turn to their role in shaping the grandest story of all, the expansion of the universe itself. For it is through light that we see galaxies receding, and through gravity that we understand how structures still form amid the stretching fabric of space. To continue, we must step back from individual events and listen to the cosmos as a whole, watching as light and gravity together reveal the growth and fate of the universe. In the early 20th century, most astronomers believed the universe was static, an eternal backdrop where stars and galaxies moved, but the whole remained fixed. Gravity, they thought, would balance everything, keeping the cosmos steady. Yet the light from galaxies told another story, one that reshaped our understanding forever. It was light, stretched by cosmic expansion, that revealed the universe is not frozen but growing, not steady but dynamic. Gravity still shapes it, but the grand stage itself is swelling beneath our feet. The key discovery came from Edwin Hubble in the 1920s. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble measured the distances to galaxies far beyond the Milky Way. He compared those distances with the spectral lines in their light. Those lines, normally sharp fingerprints of chemical elements, were shifted toward the red. The farther the galaxy, the greater the redshift. This was not a quirk of motion alone, but a universal trend. Space itself was stretching, carrying galaxies away like raisins embedded in rising dough. The light revealed it plainly. The universe was expanding. This revelation was staggering. It meant the cosmos had a beginning, a time when galaxies were closer together, when space itself was denser and hotter. Light, once again, was the messenger. Its redshift encoded the history of expansion, stretching its wavelengths as space grew. Gravity, meanwhile, was not absent. It worked against expansion, clumping matter into stars, galaxies, and clusters. The universe was not a simple explosion, but a balance of two forces: gravity pulling inward, expansion pushing outward. Their interplay defined the shape of everything we see. The redshift-distance relationship became the foundation of modern cosmology. Hubble's law, as it is now called, states that the recessional velocity of a galaxy is proportional to its distance. In words, the farther away a galaxy is, the faster it appears to be moving away. This was not just motion through space, but the expansion of space itself. Light traveling across that expanding fabric was stretched. Its wavelengths lengthened, turning blue light into red, visible light into infrared, and so on. Every photon arriving on Earth carries the imprint of this stretching, a silent testimony to the growing universe. At first, the idea of an expanding universe was met with resistance. Even Einstein had introduced a cosmological constant into his equations to preserve a static cosmos. When he learned of Hubble's discovery, he reportedly called that constant his greatest mistake. Yet the data were undeniable. The redshifts could not be explained by ordinary motion. They pointed to a universe in flux, one that began in a fiery birth we now call the Big Bang. Light, interpreted through gravity's equations, revealed a cosmos with a history. As decades passed, the evidence deepened. The discovery of the cosmic microwave background in the 1960s provided direct confirmation of a hot, dense origin. The faint glow of that early light, stretched into microwaves by billions of years of expansion, matched the predictions of the Big Bang. Gravity had shaped the small fluctuations, turning them into the seeds of galaxies, while light preserved them as a record across time. The story of expansion became one of the central truths of science, binding together the roles of gravity and light. Today, we see this expansion in every spectrum. Distant galaxies glow in infrared because their visible light has been stretched beyond our eyes. Quasars and gamma-ray bursts arrive dimmed and reddened by their long journeys through swelling space. Even the most ancient photons of the cosmic microwave background carry the mark of expansion, their wavelengths elongated by a factor of 1,000. Without light, the expansion would be invisible. Without gravity, the universe would be featureless. Together, they tell us that the cosmos is both dynamic and structured, a vast stage still unfolding. The discovery of expansion also reframed our place in the universe. If all galaxies are receding, it does not mean Earth occupies a central spot. The expansion is uniform, like dots on an inflating balloon, where every dot sees all others moving away. There is no center, only the fabric of space itself growing. Light shows us this symmetry, and gravity ensures that within it, galaxies still coalesce, stars still ignite, and planets still form. We are not in a special place, but we are part of a special story, one where the whole universe evolves. The wonder of this realization cannot be overstated. The night sky is not static. Every photon that reaches us has been altered by expansion, its wavelength stretched across billions of years. When we catch that light in our telescopes, we are not only seeing distant objects, but also reading the tempo of the cosmos itself. The universe is alive with motion, its heartbeat carried by light, and its shape sculpted by gravity. To follow this further, we must examine how expansion and gravity compete, how galaxies form within a universe that is always stretching, and what this means for the fate of everything we know. The expansion of the universe might suggest a picture of galaxies endlessly drifting apart, their bonds weakening as space stretches. Yet gravity complicates this vision. While the large-scale fabric of the cosmos grows, local regions resist the pull. Matter clumps, stars ignite, and galaxies form. Expansion sets the stage, but gravity writes the script upon it, sculpting the luminous islands that dot the cosmic sea. Without gravity, the universe would be a thin fog of particles spread ever thinner. With it, the universe is structured, filled with galaxies, clusters, and the cosmic web that binds them. Light is our witness to this interplay. When we observe distant galaxies, their redshift tells us how fast they are receding, but their shapes and clustering reveal gravity's influence. Galaxies are not scattered at random but arranged in filaments and nodes, forming a vast network billions of light years across. Light carries these patterns to us, showing that gravity has woven structure even as expansion has carried matter outward. The galaxies themselves are like frozen notes in a grand composition, their positions revealing the balance of push and pull across cosmic time. Consider a galaxy cluster. It is a collection of hundreds or thousands of galaxies bound by their mutual gravity, resisting the universal expansion within their borders. If expansion alone ruled, these systems could not exist. But gravity is strong enough to counteract the stretching of space locally. The light from galaxies within clusters tells us this truth, showing them orbiting one another rather than receding. Clusters become laboratories of cosmic balance, where expansion and gravity meet face to face, and gravity prevails. Yet even clusters are not isolated from the larger flow. Over billions of years, the space between clusters grows as expansion carries them farther apart. Light from one cluster to another must cross an ever-widening gulf, and by the time it reaches us, it is stretched and reddened. This is why distant clusters appear dimmer and redder than nearer ones, their photons bearing the marks of both their intrinsic glow and the expansion of space itself. The light does not simply describe the clusters, it records the entire journey, encoding the tempo of expansion in its wavelength. On the scale of galaxies themselves, light tells another part of the story. Within spiral galaxies, the stars orbit their centers, balanced by gravity against the outward pull of motion. Yet when we measure the spectra of their light, we find that stars in the outer regions move too quickly to be explained by visible matter alone. This is the signature of dark matter. Unseen, but gravitationally essential. Here too, light and gravity work together, the redshift of spectral lines, revealing the hidden scaffolding that allows galaxies to form and persist in an expanding universe. Even more subtle are the baryon acoustic oscillations, faint ripples frozen into the large-scale distribution of galaxies. These ripples are relics of sound waves that traveled through the hot plasma of the early universe, their imprints carried forward by light in the cosmic microwave background. As matter clumped, gravity amplified these patterns, and expansion stretched them across space. Today, we detect them as slight preferences in galaxy separations, measured by analyzing light from millions of galaxies. These ripples serve as a cosmic ruler, telling us not only how galaxies clustered, but also how fast the universe expanded over time. The story is not only about structure, but about rhythm. Expansion dictates the beat, but gravity introduces harmony, creating the structures that endure. Light, stretched into redshifts and patterns, carries the full score. Each photon arriving at our telescopes has been altered by both forces, its wavelength, a ledger of expansion, its path bent by gravity. By reading these photons, we reconstruct the history of balance between growth and collapse, dispersal and clustering. This partnership reveals a profound truth. The universe is not dominated by one force alone, but by the dialogue between expansion and gravity. Expansion ensures that the cosmos evolves, never static, always stretching. Gravity ensures that within that growth, structures form, stars burn, and life emerges. Without expansion, the universe might have collapsed back into itself. Without gravity, it would have remained a formless haze. Together, they sculpt a cosmos filled with both vastness and detail, a dynamic arena alive with galaxies. As we gaze deeper, we see not only the past, but the ongoing contest. Expansion is accelerating, driven by dark energy, while gravity continues to bind galaxies into clusters and clusters into superclusters. The light from these systems shows us both stories at once, the pull inward and the push outward, encoded in redshifts, distortions, and patterns across the sky. To understand the future of the cosmos, we must follow this dialogue to its conclusion, asking which will prevail, gravity's embrace or expansion's flight. The expansion of the universe is not a simple tale of everything flying apart into emptiness. It is a balance, a tension between gravity's inward pull and the outward swell of space itself. The ultimate question is not whether the universe expands, it does, but how that expansion unfolds over time and what it means for the future. For a long time, scientists wondered if gravity would eventually slow the expansion. If the cosmos contained enough matter, perhaps galaxies would one day stop receding, turn back, and collapse into a final big crunch. In such a universe, Light would carry the story of contraction, spectral lines shifting not only to the red, but eventually back toward the blue as galaxies fell inward. The end would mirror the beginning, born again from collapse. But observations tell us this is not our fate. In the late 1990s, two teams studying distant supernovae discovered that galaxies are not merely drifting apart, they are accelerating. Expansion is speeding up, driven by something we call dark energy. Light from those supernovae was dimmer than expected, stretched more than gravity and matter alone could explain. Photons crossing billions of light years revealed a cosmos not slowing but racing ever faster into its future. This acceleration reshaped cosmology. If it continues, the universe will not collapse, but expand forever. Galaxies beyond our local group will recede faster than light can bridge, disappearing from view. Their photons, stretched by expansion, will never reach us. Already, many galaxies are beyond our reach, their light forever trapped by the acceleration of space. In trillions of years, only the galaxies bound to our own cluster will remain visible. The universe will grow lonelier, its grand web thinning into isolated islands adrift in darkness. Gravity, however, will continue to act locally. Stars will burn, galaxies will evolve, black holes will form and merge. Within each bound system, gravity remains sovereign. Light from these events will still travel across space, but the cosmic stage on which it performs will be one of ever-widening emptiness. The dialogue between light and gravity will persist, but the audience will shrink as expansion carries the rest of the cosmos beyond our horizon. This vision is sobering yet awe-inspiring. The fate of the universe is written in the light we observe today, in the redshift of galaxies and the fading glow of supernovae. Gravity shapes the structures that endure, but expansion sets the long arc of history. Together, they determine not only what the universe looks like now, but what it will become. As we ponder this future, we realize that the interplay of light and gravity is not just about structure and expansion. It is about destiny. Their combined story stretches from the first moments of the Big Bang to the ultimate fate of all things. To follow it further, we must imagine what lies ahead. Scenarios of heat, death, Big Rip, or eternal cycles. The next chapter asks, what happens when gravity keeps sculpting, but expansion never ceases? When light grows faint, but never fully disappears? And when the cosmos confronts its future, the universe is not static, and neither is its destiny. The same forces that sculpted galaxies, stars, and planets will continue to shape the cosmos for eons beyond human imagination. Gravity and light, our two great architects, are not finished with their work. But as expansion accelerates under the influence of dark energy, we face profound questions. Will gravity eventually overcome expansion, pulling everything back together? Will dark energy continue its relentless push, tearing the cosmos apart in a big rip? Or will the universe coast toward a quiet, frozen heat death, with light as its last faint whisper? To begin answering, we must consider the balance between matter, gravity, and expansion. Gravity is conservative, always pulling inward, always gathering. It binds stars into galaxies, and galaxies into clusters. Even in a universe that expands, gravity keeps local structures intact, creating islands of order amid growing emptiness. Light shows us this every day, carrying the evidence of galaxies that resist expansion within their halos of dark matter. Wherever gravity dominates, photons still race freely, illuminating structures that endure. Yet expansion itself is not slowing. Observations tell us that dark energy makes up about 70% of the universe's total energy. Its effect is to accelerate expansion, driving galaxies apart at an ever-increasing pace. In such a universe, gravity can never win on the largest scales. Over tens of billions of years, galaxies beyond our local group will vanish from sight, their light stretched into wavelengths too long for any conceivable detector to catch. Light itself will be outpaced, unable to bridge the ever-widening gulfs of space. The cosmos will appear emptier and quieter, even as gravity continues to sculpt within each bound system. This scenario leads to what physicists call heat death. Stars will eventually exhaust their fuel, leaving behind white dwarfs, neutron stars, and black holes. Over trillions of years, these remnants will cool and fade, emitting their last photons into a universe growing ever darker. Gravity will continue to merge black holes, and Hawking radiation may, over unimaginably long timescales, evaporate them too. Light will persist in these processes, but each pulse will grow weaker, stretched across space that expands without end. The final future would be a thin, cold bath of photons, the universe's last faint glow. There are other possibilities. If dark energy is not constant but changes with time, the universe might one day rip itself apart. In the Big Rip scenario, galaxies, stars, planets, and even atoms would be torn as space accelerates beyond all bounds. The timeline depends on the exact nature of dark energy, which we still do not fully understand. Light from distant supernovae suggests acceleration is steady, but small changes could tip the balance toward a more catastrophic fate. Should a Big Rip occur, photons themselves would no longer exist, torn from their wavelengths as space loses all coherence. Gravity's structures would disintegrate, leaving only the void. A third possibility is that expansion may eventually reverse. If dark energy decays or changes sign, gravity could slow and halt the outward motion, pulling the universe back together. This big crunch would mirror the Big Bang in reverse. Light would grow bluer instead of redder as galaxies approached one another, their photons compressed by contraction. Stars and galaxies would collide, and finally all matter and energy would collapse into a single dense state. Whether such a reversal is possible remains uncertain, but the equations of relativity allow it. If it happens, gravity will have the final word, reclaiming everything light has revealed. Each scenario reminds us that the cosmos is not eternal in its current form. It evolves, and its future is tied to the interplay between gravity and expansion, revealed through light. Every photon we catch today carries hints of which path lies ahead. The cosmic microwave background, the redshift of galaxies, the clustering of matter, all are data points in the great question of fate. Light is our oracle, gravity, the force behind its prophecy. Though these futures may seem remote, they are part of the same story we live in now. The same gravity that holds Earth to the sun, the same photons that warm our days and fill our night sky, are the forces deciding the fate of the entire cosmos. To think of them only on human scales is to miss their grandest roles. They shape not just our present, but eternity itself. As we push forward, the ultimate question grows sharper. What happens to light in the final cosmos? Whether fading into heat death, shredded in a Big Rip, or compressed in a big crunch, photons remain the key. They will be the last messengers, the final storytellers of the universe's history. To follow this thread, we must explore each fate in turn, guided by the same partnership that has carried us this far, gravity shaping the stage, and light narrating the play. The vision of a universe drifting toward heat death is both chilling and fascinating. In this scenario, gravity continues to shape small scales, but expansion dominates the grand stage. Stars exhaust their fuel, one by one, leaving behind fading remnants. White dwarfs cool into black dwarfs, neutron stars grow cold and dark, and black holes consume what remains of matter. The cosmos becomes a graveyard of objects, each radiating fainter and fainter light into space that stretches endlessly. The timescales are staggering. Our own sun will shine for another 5 billion years before swelling into a red giant and then collapsing into a white dwarf. But the story of heat death unfolds not over billions, but trillions upon trillions of years. In that future, stars will no longer form, as the gas needed to create them will have been consumed or locked in remnants. Gravity will continue to merge stars and black holes, but no new light will be born. Instead, existing photons will drift farther apart, their wavelengths stretched until they become indistinguishable from the cold background. Even black holes, the most enduring objects we know, are not eternal. According to Hawking's theory, they radiate faint particles through quantum effects at their horizons. Over unimaginable spans of time, this Hawking radiation will cause black holes to evaporate. A stellar mass black hole might take 10 to the power of 67 years to vanish. The supermassive black hole at the center of our galaxy could take 10 to the power of 100 years. When they finally evaporate, they will release their mass as faint radiation, adding to the thin bath of photons filling the cosmos. By then, the universe will be dark in every human sense. No stars will shine, no galaxies will glow, only radiation too faint for eyes or instruments. Light will still exist, but stretched and weakened until it is nearly indistinguishable from nothingness. Gravity will have done its work, gathering and collapsing, but expansion will ensure that even the faintest signals are diluted into near silence. The final cosmos will be a thin, uniform sea of energy, the ultimate equilibrium where nothing more can happen. This end is not violent but quiet. It is a fading, a cooling, a dissolving of structure into stillness. In such a universe, time itself loses meaning, for nothing changes. Light, once the vibrant storyteller of galaxies and stars, becomes a whisper stretched across infinite distances. The heartbeat of the cosmos slows until it is indistinguishable from silence. For others, it is beautiful, a testament to the inevitability of entropy and the power of natural law. Yet heat death is not the only possible fate. If dark energy grows stronger, the universe could face a big rip, an ending far more dramatic. In this case, expansion would accelerate without limit, overcoming even local gravity. First, galaxies would be torn apart, then stars ripped from their orbits, then planets shredded from stars. In the final moments, even atoms would be pulled apart, and light itself would cease to exist as wavelengths were stretched beyond coherence. The cosmos would not fade but unravel, a crescendo of destruction, ending in nothingness. Alternatively, if dark energy is not constant but decays, the expansion could one day slow, halt, and reverse. Gravity would regain the upper hand, pulling galaxies back together in a great collapse. Light, in such a universe, would grow bluer instead of redder as galaxies approached. The final epoch would be a firestorm of collisions, ending in a singular crunch where all matter and energy are compressed again. Some theories suggest this could spark another cycle of expansion, a new Big Bang born from the ashes of the old. If so, gravity and light would begin their dance anew, weaving another cosmic story. Each scenario, the slow fade of heat death, the catastrophic tear of the Big Rip, the fiery rebirth of the Big Crunch, depends on the nature of dark energy, a mystery we have only begun to probe. Yet all share a common theme. Light will carry the evidence, and gravity will guide the outcome. Even in the universe's final moments, photons will be the last to tell the story. Whether stretched into silence, ripped apart, or compressed into rebirth, these fates remind us that the cosmos is not timeless. It has a history and a future, written in the interplay of light and gravity. We are fortunate to live in an epoch when stars shine, galaxies glow, and photons bring us news of distant worlds. This golden age will not last forever, but it is ours, and it connects us to the great arc of cosmic destiny. To continue, we must ask what role humanity plays in this story, and how our own existence is bound to the same partnership that shapes galaxies and determines the fate of time. Over the span of trillions of years, the future of the cosmos narrows to three grand possibilities: endless fading, catastrophic tearing, or cyclical rebirth. Each of these futures is written into the equations of relativity, but the choice among them depends on the nature of dark energy, a mystery still unsolved. What unites them all is the role of gravity and light as the central players, the forces and messengers that will shape not only the present, but the ultimate fate of reality. If the universe proceeds toward heat death, light will be the last survivor. Even as stars die and galaxies dissolve, photons will continue to drift outward, stretched thinner and thinner by expansion. They will grow faint, cold, and long. Yet they will remain, a final whisper of the cosmos, long after every star has faded. Gravity will continue its quiet work, merging black holes and allowing Hawking radiation to release their mass back into the universe. In this future, the last traces of gravity's sculpting will be carried on the wings of light, until both fade into a uniform stillness. If instead the cosmos faces a big rip, the story is more violent. Expansion accelerates without end, eventually tearing apart galaxies, then stars, then atoms. In this finale, even light itself cannot survive, its waves shredded by a space that outpaces all coherence. Gravity's structures unravel, and photons lose their meaning. This is a future of dissolution, a universe that destroys itself in its own runaway growth. Here, neither light nor gravity wins, for both are erased in the end. And if the universe one day collapses in a big crunch, light will be transformed. As galaxies fall together, photons will be squeezed into shorter and shorter wavelengths, shifting from red to blue, from cold to fiery. Gravity will dominate, pulling all into a final, dense singularity. The cosmos will end in a blaze of energy, perhaps to give rise to another beginning. In such a cycle, gravity and light are eternal partners, weaving story after story across infinite ages. These futures may seem remote, but they remind us of something profound. The universe is not eternal in its present form. It is dynamic, with a past and a future shaped by the same interplay that governs our everyday lives. The sunlight warming Earth, the starlight filling the night sky, the gravity that binds us to our planet, all are part of the same cosmic arc that determines eternity. Our moment is one verse in a much larger song, one in which light and gravity are the composers and performers alike. The destiny of the cosmos is beyond our control, yet its story is not beyond our comprehension. We may not live to see the end, but we live to know it, to imagine it, to marvel at the scale of forces that guide it. In the end, what matters most is not which future awaits, but that we are here, now, in an epoch where the universe is vibrant with light and rich with gravity's structures. We can see galaxies, study stars, and read photons that have traveled billions of years. We are privileged witnesses to a cosmos still alive with energy. And so, as the future unfolds in ways we can only imagine, the message is clear. Gravity will keep sculpting. Light will keep telling the story. Even in silence, even in darkness, their interplay defines the fate of everything. From the first moments of the Big Bang to the last photon of heat death, or the final blaze of a big crunch, the universe is their creation. To move toward the conclusion of our journey, we must bring this cosmic story back to ourselves, to see how the same forces that shape eternity also shape our existence, our world, and our place within the grand design. For billions of years before life arose on Earth, gravity and light were already at work, sculpting the cosmos that would one day give us a home. Stars ignited, their photons racing outward through the cold night of space. Galaxies gathered, their shapes carved by invisible halos of dark matter. Gravity pulled together the atoms of hydrogen and helium, and light burst forth as those atoms fused in stellar cores. Without this partnership, there would be no planets, no warmth, no chemistry of life. Our very existence is an echo of their interplay. The sun that sustains us is itself a balance between gravity and light. Gravity compresses its core, forcing atoms so close that nuclear fusion becomes inevitable. Fusion releases energy as photons, which scatter through layers of gas before emerging into space as sunlight. Every moment, trillions upon trillions of photons pour onto Earth, warming its surface, driving weather, and fueling photosynthesis. Plants trap those photons in chemical bonds, creating the energy that sustains all life. Every bite of food, every breath of oxygen, every beat of our hearts is powered by sunlight. We are children of light, made possible because gravity sculpted a star to shine. And yet, gravity is no less vital. It holds Earth in orbit, keeping us at a stable distance where water can remain liquid and life can thrive. It binds the atmosphere around us, anchoring the air we breathe. It shapes the tides through the pull of the moon, rhythms that influenced early life in the seas. Without gravity, photons from the sun would flood a barren rock, unable to sustain the delicate balance of warmth and chemistry we require. Life is not born of light alone, but of light held within the embrace of gravity. Our very bodies carry this heritage. The calcium in our bones, the iron in our blood, the carbon in every cell. These elements were forged in stars. Gravity crushed atoms into heavier forms, and light carried the evidence of that creation outward. When those stars died in supernovae, their debris seeded new systems. Earth itself is a child of starlight and gravity, a planet assembled from dust and gas enriched by stellar death. Every atom of us has been through that cycle. To be human is to be built of stardust, assembled by gravity, illuminated by light. Even our perception of reality is defined by them. We see because photons strike our eyes, their wavelengths translated into color and shape. We stand because gravity pulls on our bodies, giving us weight and orientation. We measure time by the oscillations of light in atomic clocks, and our lives unfold within the gravitational rhythms of days, months, and years. Light and gravity are not distant abstractions. They are the fabric of our experience, as intimate as breath, as constant as heartbeat. The story of the cosmos is therefore not separate from us. It is our story. The same equations that describe galaxies describe the orbit of Earth. The same photons that cross billions of light years to reach our telescopes are kin to the photons that warm our skin. The interplay of gravity and light does not only shape the universe, it shapes us, our history, and our future. As we look upward, we are reminded of this kinship. The night sky is not only beautiful, but revealing. Every star is a fusion furnace, balanced by gravity and glowing with light. Every galaxy is a sculpture of dark matter and luminous stars. Every arc of starlight bent by gravity is a testament to the laws that govern all things. To gaze at the heavens is to see the forces that made us, the cosmic architects still at work. The awe we feel when we contemplate these truths is not accidental. It is the recognition that we are connected to the universe in the deepest way. Gravity and light are not only external forces, they are our origins, our sustenance, our destiny. To understand them is to understand ourselves. To deny them would be to deny our very existence. And yet, there is more. Beyond their physical roles, gravity and light inspire meaning. They remind us that even in darkness, light persists, carrying stories across time. They remind us that even amid expansion, gravity holds things together. These lessons are not only cosmic but human, metaphors written into the physics of reality. In their interplay, we find a mirror of resilience and connection. To continue this reflection, we must draw the story to its close, returning to the grand narrative with which we began. Gravity shaping the stage, light telling the story. Together, they are not only the architects of galaxies, but the architects of our place within the cosmos. Their partnership is the reason we exist, the reason we can wonder, and the reason we can tell this tale at all. Light and gravity do not only sustain us, they also guide our quest for knowledge. Every science we have built, every telescope, every equation, every philosophy of the cosmos is anchored in their interplay. We learned the laws of motion by watching how objects fall under gravity's pull. We uncovered the chemistry of the stars by analyzing their light, breaking it into spectra that revealed the elements within. Our understanding of reality, from the orbits of planets to the expansion of the universe, is written in the dialogue between these two forces. Consider astronomy, the oldest science. The ancients tracked the paths of the planets, their motion governed by gravity, though they did not yet know the name of the force. They charted the stars, shining by the light of fusion, unaware of the physics within. Their calendars, rituals, and myths were shaped by cycles of gravity and light, the rising of the sun, the phases of the moon, the shifting constellations through the seasons. Our earliest efforts to find order in the world were efforts to read the story that gravity and light were telling. In modern times, technology itself is an application of this knowledge. The global positioning system depends on gravitational time dilation, with atomic clocks correcting for the warping of time by Earth's mass. Fiber optic cables carry light pulses across oceans, encoding information in the very photons that once carried starlight across the void. Solar panels harness the sun's photons directly, converting them into electricity. Every spacecraft launched into orbit is a negotiation between light and gravity. Light guiding its navigation through radio signals, gravity shaping its trajectory around planets and moons. Even our philosophical perspective is shaped by these discoveries. To know that gravity bends light is to know that reality is not rigid but curved, that space and time themselves are dynamic. To see galaxies receding in redshift is to realize that the universe has a history, that it was born, and will have a future. To witness gravitational waves is to feel the universe vibrate, a reminder that we are part of a living cosmos. These truths change how we see ourselves. We are not separate from the universe, but woven into its very fabric, participants in the same laws that sculpt galaxies and bend photons. Our art and imagination, too, reflect this awe. Painters have captured the glow of the sun and stars. Poets have written of the pull of gravity and the journey of light. Science fiction dreams of harnessing gravity for travel and bending light for invisibility. Even the language we use, speaking of enlightenment as illumination, or love as a force that draws us together, echoes the physical realities of gravity and light. They are metaphors as much as they are forces, shaping culture as well as cosmos. Yet perhaps their greatest gift is perspective. Through light, we see that the universe is vast, billions of galaxies beyond our own, each filled with billions of stars. Through gravity, we understand that despite this vastness, everything is connected, drawn together by the same invisible hand. We are small, yet not insignificant. The same laws that sculpt the largest clusters also govern the fall of an apple, the orbit of the moon, the weight we feel in our bones. To grasp this unity is to find both humility and belonging. As we look ahead, our future will be shaped by how we continue to work with these forces. The next generations of telescopes will use light to peer deeper into time, to see the first galaxies, to measure the fingerprints of dark energy. Gravitational wave observatories will tune their ears to lower frequencies, listening for the mergers of supermassive black holes. Together, they will extend our senses farther than ever before. Light and gravity will continue to be our guides, expanding the frontier of human knowledge. And as we expand into space, their roles will become even more personal. Astronauts on Mars will rely on sunlight for power and warmth, and on gravity for stability in orbit and landing. Deep space missions will navigate by the pull of planets and the timing of light signals. Even as we leave Earth, we remain bound to the partnership that made us. Light will illuminate our way, and gravity will chart our course. These reflections lead us to a final truth. The story of gravity and light is not only about the universe, but about us within it. It is a story of survival, of curiosity, of wonder. It is a story of science and art, of myth and measurement. It is the story of humanity discovering that it is made of the same forces that govern the stars. And as we near the end of this journey, we see that the cosmos is not only out there, but within us, carried in our atoms, our senses, and our imagination. Gravity and light have led us across the vast arc of cosmic history, from the first whispers of the Big Bang to the imagined silence of the far future. They are not abstract forces distant from our lives. They are the architects of everything we know, the builders of galaxies, the sustainers of stars, the sculptors of planets. Without gravity, matter would never have gathered to form suns and worlds. Without light, energy would never have spread. Life would never have arisen, and the universe would remain invisible even to itself. They are not simply parts of the story, they are the story. As we stand beneath the night sky, every star is a reminder of this truth. Each one is a balance of gravity pressing inward and light pushing outward. Every galaxy is a frozen moment in the dialogue between expansion and collapse. Every photon that reaches us carries the memory of its journey across space-time, bent and redshifted by gravity, a message written in the language of the cosmos. And every orbit, every tide, every fall of an apple is gravity's quiet insistence that nothing is separate, that all things are connected. We are woven into their interplay, our lives possible only because of their eternal partnership. The great questions of existence: where did we come from? Why are we here? What is our destiny? Are answered, at least in part, by their dance. We came from starlight, forged in furnaces lit by gravity's pressure. We are here because light sustains us, bound by gravity to a planet in the habitable warmth of its Sunday. Our destiny is tied to the same expansion and collapse that governs galaxies, to the same fading or renewal that will decide the fate of the universe. To know gravity and light is to know ourselves. To see that we are not spectators, but participants in the grand unfolding. This realization is humbling, yet also empowering. Though we are small, the laws that govern the stars govern us. Though we are fragile, we are made of stardust, our atoms forged in cosmic fire. Though our lives are fleeting, the light we see connects us to times and places far beyond our own. The cosmos is vast, but it is not alien. It is our origin, our stage, our inheritance, and so the story closes where it began. Gravity shapes the stage, light tells the story. Together they weave the fabric of reality, from the smallest particle to the largest cluster, from the first moment of creation to the final fate of time. They are the twin architects of existence, the unseen and the seen, the silent curve of space-time and the brilliant flash of photons. They are the reason there is something instead of nothing, order instead of chaos, life instead of emptiness. As long as we can wonder, as long as we can look up and see the stars, their story continues in us. For we, too, are their creation, and in telling their tale, we tell our own. The universe is not only illuminated by light and bound by gravity, it is given meaning through our eyes, our minds, our voices. In knowing them, we find our place within the grand design, a fleeting yet eternal part of the cosmic symphony.